invited you this Friday on our ICANX Talks stage. Yeah, as every Friday we have this program, we invite the speakers to deliver the talks across the world and the universe. Today is really special because today we have two of us here. One is me, Alice Zhang from Peking University. Another is my best friend. Many of you know her very well, and he's the most famous journalist. And he has her super light journal. And Professor Bai Yuhong. Yeah, Yuhong, please. Yuhong, you're mute.
Unmute yourself, Professor Bai.
Okay.
Hello. Hi. Can you hear me?
Yes.
Yeah. Hello, everyone. Welcome to 2021 Rising Stars of Light. Representing my colleagues from Life Science and Application, E-Light, and Life Advanced Manufacturing, I'd like to first thank all the committee members, hosts, nominators, and applicants for making Rising Stars of Light possible and a great competition for our brilliant young scientists. Second, I'd like to acknowledge UNESCO's International Day of Light for highlighting Rising Stars of Light as a featured event. And third, I hope all of the speakers and the audience can enjoy the talks today and next Friday. Best luck to all of you. Thank you.
Thank you, Yuhong. Yeah, that's what's happening this week. We have the 2021 Rising Star of Light. So this was a special version, and last year we have this Rising Star of Light on ICANX2. And we see many of the best, young scientists was nominated. So this was from May to August. We got nominations from the whole world, from whole continentals. There are many from US, Australia, Asia, and Europe. And eventually we selected by the committee and to get the peoples to come here. So our committee members have Professor Antonio Azakan from University of California, Los Angeles was a chair. We have co-chairs, Professor Jagdish from Australia, Professor Lu was from University of New York. We have Cao Hui was from your university. We have Yang Lan from University of St. Louis. And we have Chaoyang Lu was from University of Science and China, Technology of China. We have a Professor Qiu Min from Westlake University. And all these committee members are hardworking and selected the finalists. The finalists, 10 from all the global nominations came here. And they from different universities, different part of the world, and they will give the talk on this ICANX talks. And this is not only a talk, it's a competition because they were evaluated by the committee members too. We divided it into two sessions. Session 1 is today. Today we have 6 members. And next week, next Friday, we have another 4 get on the stage. Also, next week we'll have our award ceremony. So by doing this well, we got 2 hosters of the Rising Stars final. First week, this week is Professor Liang Caicao from Tsinghua University. And next week, our host will be Chen Ziguo, the E-Light, the general office. She will in charge of next week's final. So, yeah, without further ado, we invited our first moderator and host, Professor Liang Caicao, to chair today's session. Yeah, Professor Cao, please. Yeah, you're okay.
Hi, everybody. Good morning, good evening. You're welcome to join this big event. So it's my great honor and pleasure to chair this session. So in this session, we have 6 speakers. The first speaker is please turn the slides. Yeah. So today we have 6 speakers. The first is Professor Howard Lee from University of California, Irvine. The title is Gap Topology, Zero Index Metal Surfaces and Optical Fibers. Let's welcome Howard, please.
Hey, hello everyone. Just want to make sure, can you see my site well?
Sure.
Okay, sounds great. Yeah, thank you, Lanchao, for the introductions. And I'm Howard Lee from University of California, Irvine, from the Physics Department, and also Batman Mason Institute. At the same time, I'm also the OSA or Optical Ambassador. So first of all, I'd like to thank you, the organizer, to invite me to be here to share with you about my research. At the same time, also participate on this Rising Star of Light campaign here. And at the moment, I hope everyone is doing well. So I know we have a quite difficult years, but we are getting better now, and hopefully we are getting back to normal soon, so we can actually meet each other like in person soon, maybe in the next couple of months or even next year. So what I'm going to tell you today is the research from my research group. We have been working for some time on this kind of really interesting thing called a zero index material. And I will tell you how we actually can, for example, making it tunable at the same time integrating for metal surface or even into an optical fiber platform. So let me first tell you a little bit what exactly this zero index material, or this sometimes called this Epsilon near zero material as well. So Epsilon here means the permittivity. So that means this material have permittivity close to zero. And typically, you know, in metal, you have a permittivity negative in the visible range, and dielectric, you have a permittivity about zero. And this ENC materials actually means you have a permittivity of the material close to zero in certain frequency of light or certain wavelength of light here. So in this really special regime, you actually can find a lot of really fascinating, really interesting optical property and physics out of this ENC regime here. For example, if we just try to take a simple look on a simple boundary condition, if your epsilon close to zero, your field can enhance quite significantly. At the same time, if your epsilon close to zero, your refractive index close to zero, that means you can have a really high phase velocity. That's why this kind of ENC regime actually can find a lot of really fascinating, really interesting extreme optics in this kind of material here. And that's also why in the last couple of years, you can find a lot of really exciting application or property have been studied in this kind of ENC medium. For example, short light, perfect absorption. You need property, publication or content property. For example, Later and Gator and Andrea Lu also in this audience here is actually in pioneer on this study on this kind of ENC material. At the same time, quite interesting magneto-optical property or enhancing emission, controlling emissions. Or quite excitingly, recently also find they have a really high non-linearity in this kind of ENC material, which could be used for example, optical switching, harmonic generation, etc. So you can see a lot of really excitement here, a lot of interesting physics application you can find. And also most of them are actually quite recent, just last couple of years, a lot of exciting report in this area here. So that's why I would say this is actually one of the quite hot topic or quite exciting topic for optics and photonics in the last couple of years. But still, if you try to take a look on most of the report so far, what you find actually most of them, they are actually passive structure. What I mean, actually, once you fabricate the structure, you cannot change the optical property anymore. So at the same time, most of the study also focusing on panel structure, for example, film structure, metal surface structure. Also, there are no efficient way to nano engineer material, or at the same time, for example, some of the mechanism enhancement on, for example, non-linearity emission, they actually have not been completely understood so far. So this is exactly what our motivation here. We actually want to make develop some tunable ENC material and device at the same time using nano engineering to control this ENC material at the same time ENC property, for example, the field confinements, non-linearity or emission. And finally, I also want to integrate this ENC material to different platforms, for example, optical fiber platform, or used for different application here. So this is actually the motivation for our study, and this actually go to the outline of my talk. I will first tell you here how we actually can make some tunable property or nano engineering this kind of ENC material. And then in the second part, I will change the gear a little bit to tell you how we're actually integrating this kind of ENC material into optical fiber platform. So let me first tell you about the tunable or nano engineering property of this material. So as I say, Epsilon near is a ENC material with permittivity close to zero. And you can find some material, for example, conducting oxide material. If you look at the dispersion, you actually find there's a zero crossing point, and this is exactly the ENC point we are talking about. And you can also see that actually this ENC wavelength is around near infrared or close to visible. So actually we can use this to even optical application as well. And that's why we have been using this conducting oxide material quite a lot for studying this kind of ENC property and device application here. So one of the good things for this kind of a conducting oxide material, actually you can have a tunable optical property. To show you the tunable optical property, I'm showing here is a permittivity, real part of permittivity against the frequency or against the wavelength of light, using a standard 3-electron Judah model with a capital N carrier concentration and plasma frequency here, assuming indium tin oxide material. And you can see that by changing the carrier concentration of the material, can shift the dispersion to different wavelength. And also, if you look at the optical frequency, you can see that actually you can have a positive permittivity, that means a dielectric property, or negative permittivity, that means a metallic property, depending on the carrier concentration of the material. And also, if you look at the zero crossing point, the ENC point, you can shift all the way from maybe near infrared to close to visible range as well, depending on the carrier concentration. So that means it's really good. By changing the carrier concentration of the material, you can change the optical property at the same time changing, for example, the ENC property of this material. So to change the carrier density of the material, you can do it, for example, by fabricating conditions. But at the same time, you can do it, control it by, for example, electrically gating the material. What you can do is, for example, constructing a gate tunable structure with a MOS transistor type of structure with a metal insulator and semiconductor here. When you apply the voltage, you accumulate the electron. As a result, you can increase the electron density. As a result, you will change the optical property of this material here. So this is the way we try to do is this kind of active control on this material is using this gate tunable structure to tune the material at the same time the ENC property here. So then using this effect, previously we was able to demonstrate, for example, making a tunable metal surface, integrating to a metal surface, applying the voltage, and coupling to the ENC resonance, we're able to achieve quite large pi phase shift modulation, applying a couple of volts here. And you can use this tunable metal surface to beam spin the light actively as well. And at the same time, we also integrate that to a plasmonic slot waveguide so that we can apply the voltage actively modulating the signal. And we got a modulation strength about 2.7 dB per micron by applying a couple of volts here. So which is a quite high modulation strength at that time, like one of the highest modulation strength you can find in a plasmonic modulator. And at the same time, we're also able to demonstrate, for example, making a tunable color filter, having an MIM structure. You apply the voltage, you can change the transmission as a color filter effect here. Again, it's coupling again to this ENC resonance here. So you can see that really using this gate tunability, you can really actively control this kind of nanophotonic structure. But here, I actually want to focus a little bit more on the ENC mode excitation itself, other than just combining metal surface or plasmonic structure. So to excite this kind of ENC mode of the material, what you need is actually just using a prism and then coupling with a certain angle, and you will be able to excite this kind of so-called ENC mode here. And once you're able to excite this mode, what you find, you actually have a really high field confinement in all this ENC material. Basically, all the field will confine this ITO or this ENC layer here. And as a result, you can also have a perfect absorption. You can see that you have a perfect absorption depending on carrier concentration. You can shift the absorption band here. And just keep in mind, to excite this mode, you can actually have a really thin film. So excitation condition could be lambda divided by 50 or 100. That means if you are looking at the visible range, your thickness could be only 10 nanometer thick. At the same time, you need a certain combination and angle and thickness in order to excite this mode efficiently. So what that means is that you actually need to have a really good control on the material in terms of the ENC wavelength and thickness here. So that's exactly why we try to use a technique called atomic layer deposition technique to fabricate this kind of ENC material. And the good thing for this ALD technique is as you can do it layer by layer. At the same time, in each layer, you can have an atomic layer thickness. At the same time, each layer you can actually change the property of each layer by using this ALD technique. So for example, we make the ACO material by changing the zinc oxide aluminum ratio, you can precisely control this ENC wavelength. And particularly we're targeting on around 1550 metallic communication wavelength. So just want to remind again, this technique actually allow you to really precisely control the ENC wavelength and thickness, which is quite important for this ENC optics and ENC mode excitation. At the same time, we also can get a quite good surface quality and also coating the sidewall of the metal surface because it's a conformal deposition here. So that's why we have been using this technique quite a lot to making this kind of ENC material. And just to try to show you, for example, one of the material we make a 15 nanometer thick ITO. If you look at the reflectance, you see a reflectance dip here, which is correspond to a ENC mode excitation. And you can see the amplitude is quite high, like 20 dB, which is close to 99% absorption. So you can see by exciting this mode, you can using really thin film absorb like more than 99% of light here. At the same time, if you change the carrier density, you can change the absorption band to a different wavelength as you decide. And at the same time, we're also able to demonstrate by making a multi-layer ENC material. So stacking them together, and each layer have different ENC wavelength or different carrier concentration. And combining them together, we actually can have a collective excitation of the mode. As a result, we get a broad band absorption in this case. And also, we're also able to show, for example, making a tunable absorber based on this. Applying voltage, you can tune the absorption band, have a quite large absorption modulation here. So all of this are more or less a linear property of this ENC optics. But as I mentioned to you, like one of the quite exciting property actually is the nonlinearity of the material. So that's why we have been also looking on the nonlinear effect of this material by using an ultra-fast laser pulse and using a standard so-called C-scan nonlinear measurement method here. So I will try to skip the details about this C-scan method, but just try to show you the result of this measurement on this ACO thin film with 76 nanometer thickness. And this is a nonlinear reflection and absorption coefficient N2 and beta 2 you can get. And this actually is already 5 orders of magnitude higher than fused silicon glasses. And I would say actually one of the highest nonlinearity you can find in any material. So that's why this kind of ENC material have a really interesting properties actually is the high nonlinearity here. So then what we also interested to study is actually some kind of angular dependency, because to excite this mode, as I say, they are really depending on the angle of excitation or the wavelength. So you can see a certain angle and wavelength, you can excite this mode more efficiently. And at the same time, we also try to look at, for example, the thickness dependent as well, because there are some report showing that the optical field confinement is actually inverse proportional to the square of the thickness. So that means the smaller the thickness, the higher the optical confinement. As a result, you may have a higher nonlinearity. So which is something we try to study using this ALD fabricated thin film, ENC thin film. So then this is some of the results we can see for the 76 nanometer thin film. Thinner film actually have a higher N2 nonlinear coefficient here. At the same time, you can see a quite strong angular dependency. In certain angle, you actually have a high N2 because you excite the ENC more efficiently. So that's why you can actually see a quite strong angular and thickness dependency here. But for those of you, if you are actually familiar with the field of nonlinear optics in ENC material, you may find actually rubber boys already showed some of the results a couple of years ago. They find they have a really high nonlinearity on this material at the same time. Also this kind of angular dependency, maybe not the thickness dependency, but they show the quite strong angular dependency here. It seems nothing special anymore, but what we find are quite interesting physics which haven't been observed so far in this kind of material is that actually you find there's something optical curl nonlinear high order nonlinear effect here in this material. So for example, in a normal material, if you have a delta N with a positive sign, you have a Gaussian beam, ultra fast beam propagating here, you will have actually self-focusing effect. But if your delta N change is actually negative, then you have a defocusing effect here. So then we try to look at our sample by looking at the C-scans and normalizing the C-scan trace between the closed aperture and open aperture and scanning on the C direction. If we, in a normal incident, you will see actually the transmission ratio will change from the dip to the peak when we scan on the C direction, so which correspond to a positive delta N here. But when we change the angle of the excitation, what we find, if we go to 70 degrees, we find actually instead of a dip to a peak, you actually have a peak and then dip, which actually correspond to a negative delta N here. So which is quite interesting because somehow by just changing the angle, you're actually changing the sign of this nonlinear phase change here. And we actually further do more angle, you find actually similar result by changing gradually the angle, you actually changing the sign and a certain wave angle, you actually have a higher amplitude here. So what we're actually able to find out is that we find there's quite interesting contribution from the higher order curl nonlinearity, for example, N4. And in this kind of ENC material, actually further enhancing this N4 contribution. And typically, for example, people have been observed this kind of high order curl effect in gases in really high peak power. And I would say this is actually the first time we observe it in the solid, in this kind of ENC material. And this kind of ENC actually enhancing significantly the high order term, which inducing this kind of a change of size of this nonlinearity here. So this is quite exciting. Just try to remark some of the observation we got. We have a thickness dependency. You can control the field confinement. At the same time, we observe some interesting high order curl effect and also some anomalous electronic dynamic here. So, and what we are trying to do and also planning to do is even integrating this kind of high nonlinear material to different platforms. For example, metal surface platform, we actually can coat the ENC material on the metal surface or design some interesting metal surface where you can electrically tuning the resonance as well. So at the end, maybe we can actually having a harmonic generation at the same time have an active control electrically or optically on all the phase or even amplitude here. So that could be potentially useful for ultra fast imaging, image encoding, nonlinear metal surface, or even optical switching, etc. At the same time, we also try to integrate this to a nanophotonic circuit, for example, to a plasmonic circuit. For example, taking use of nonlinearity in a coupler, you may be able to optical switching, depending on the power, you may go into the bar or cos, or even more complicated resonance structure. You can have a complicated optical switching mechanism here. So again, this is a great for nonlinear optics, but just want to mention that we also find quite interesting result recently on enhancement on the spontaneous emission based on this ENC material. So using a 2D material as an emitter with ENC on the bottom, we're able to find some enhancement here. But I don't have time to go through all the details with you. So if you're interested, you can take a look on this these two papers here. So in the next maybe 3 or 4 minutes, let me quickly mention to you a little bit how we actually integrate this ENC material, ENC optics in a completely different platform into optical fiber. So as you may know, optical fiber is a really great platform. You can transmit light for long distance with the glasses, and that's why we have a really good optical communication nowadays. And in my opinion, actually, this is one of the best innovation nowadays, because without internet, high-speed communication, I can't even talk with you online here now, or we cannot even watch the movie online, etc. So it's really important application on optical communication for optical fiber. But other than that, also for imaging, sensing, fiber laser, fiber optics have been really important. At the same time, it's quite mature technology nowadays already. But still, if you try to take a look on the optical fiber, you find you actually have a certain limitation here by the, for example, material you use or some geometry you use to guiding the light. At the same time, once you fabricate the material in the fiber joint tower, all the properties fixed. For example, phase, amplitude, polarization, etc. is fixed already. So this is exactly what we are interested in my group, is to try to find some of the nanophotonic concept, for example, metal surface, plasmonic, or ENC material, into this kind of fiber, optical fiber technology, to develop a new kind of optical fiber. We call this a meta optical fiber, so that we can advance the functionality, minimizing the size of the component, or even making a new excitation platform or application, etc. So at the same time, we also want to make it tunable as well. By applying voltage, we want to actively control some of this property as well on the fiber. So that's why in my group, we have been working on, for example, integrating metal surface, plasmonic nanowire, or even nanocircuit on fiber. And just to give you some example, for example, we're able to making a metal surface lenses, metal lens on fiber to focus the light and the end phase of the fiber. or we can actually making a metallic nanowire to excite the plasmonic resonance, focusing down to a plasmonic hotspot so that you can use for tip enhanced Wildman extraction. And just keep in mind again that this dimension is of the fibers is similar to my hair. And we are actually making nanostructure at the end phase on the core, so they are really small in the structure. So that's why we are really integrating some of the nanophotonic structure into a micron size photonic structure here. But here, actually, I want to focus a little bit more on how we're actually integrating the ENC material on fiber. So what we have been doing different platform, DC fiber, nanoball fiber, or even hollow core fiber. And the motivation here, we actually want to have a different excitation platform of the ENC material, have a longer interaction length. At the same time, we can actually have an automatic phase matching. By just coupling to the fiber mode, we can couple the ENC mode automatically without any preset. And as a result, we can also potentially making device and different novel functionality in fiber. So just give you one quick result on, for example, we code ALD using ALD to code ACL, and on the D-shaped fiber, we see a strong resonance here, which corresponds to ENC mode excitation. And we also confirm we can have a high field confinement here. And quite interestingly, actually, this kind of resonance is quite depending on the external medium as well. That's why if you change the external medium, you can change the resonance quite significantly. That's why you can use potentially as an ultra sensitive sensor. And also we demonstrate that by using the law. Okay. By using the nonlinearity, you can actually using for optical switching on a fiber, we're able to demonstrate quite decent modulation using the nonlinearity of the ENC material. Also, by constructing a gate tunable structure, you can electrically biasing with quite decent modulation here. So at the same time, we also integrating to different platforms, for example, hollow channel, right, nanoball using the ALD to coding the ACL inside the hollow fiber, or even some of the interesting anti-resonant hollow core fiber, where we can actually coding some material here. So probably my time is going up, so I just want to emphasize again, there are a lot of promise on this kind of integration. We can study the ENC material in a different platform to study, for example, nonlinear quantum property, making device like optical sensor, modulator, or even fiber laser as well, or even find some new guiding mechanism as well. So probably I don't want to summarize my talk, just want to emphasize again, there are a lot of promising area and really exciting research we can do on zero index photonics, like in terms of new science, for example, quantum emission, voltage generation, thermal emission, and nonlinear optics is a quite exciting research for ENC, for example, looking on the nonlinear dynamic, time-varying nonlinearity, ultra-fast switching. Integration is quite important, integrating the fiber, or nanocircuit, or even some of the topological structure or metal surface, and finally making device like tunable metal surface, optical switch, or even light source and ultra fast sensing. So there are a really bright future, I would say, in this kind of zero index optic, and a lot of excitement here. So that's all I want to say, and just want to quickly acknowledge my group member. Without all the hard work, I cannot tell you all the results. At UC Irvine, and recently moved from Baylor University to UC Irvine. And also acknowledge the people working together in the past couple of years in Texas, learning scholarly extraction, and also my postdoc advisor, Harry Atwater. Also my PhD advisor, Philip Russell, Marcus Submit, and they teach me how to be creative and also be motivated on keep doing research, and also other thought from Asia as well. And also the funding agency support in the past couple of years. That's all of my presentation, and really thank you for your opportunity for me to share with you the research, and looking forward to seeing you and looking forward to your question as well.
Wow, thank you, Howard. It's a very nice talk. Thank you for the very impressive talk. So now the session is open for question. Yeah, our chair, Professor Oscar, please.
Thanks. Very nice presentation, Dr. Lee. Thanks. I had a quick question regarding the last part that you showed. Can you tell us more about the typical loss values for the ENC integrated fiber optic systems that you're building, including the coupling losses and the propagation losses? What are we looking at? And also a related question is, how long can you make these devices in a repeatable way? So what is the typical length that you can create? Thank you.
Yeah, sure. So, for example, in terms of the coupling losses or the propagating losses of the fiber. So, for example, just take this example. So, the good thing here is actually you can vary the coupling of this core to this ENC medium by just changing, for example, the spacing between the core to the ENC layer. So then, for example, here we are talking about so for example, we use around 2 centimeter of the fiber. We got around 30 dB. So this is actually quite strong coupling because we actually having a cladding edge close to the core. So basically, the ENC medium is close to the core as well. So then, really depending on your separations and your overlap between the field, you actually can control this coupling here. And we can potentially even use maybe 10 centimeter of this kind of fiber for application. But in my opinion, it's like what we want to do for certainly is not a long distance communications, at least for this device here. We may actually want to just integrate a small region as an active region so that we can add the functionality here. But for example, if you're close to, let's say, coating some of this hollow core fiber as well, because the core is the ENC even inside the core of the fiber, your coupling will be even stronger as well. And at the same time, you may have different guiding mechanism as well. But in terms of the fabrications, most of the time we use the ALD technique. So we have a hollow tube fiber or capillary hollow core fiber. We put it in an ALD chamber. Then this will be depending on your chamber's length. But at the same time, you need to have the precursor, the gas to flow into the capillary. So also quite depending on your size of the hole and also how long you wait for the chemical to get into the hole. So the longest one so far we make around 10 centimeter. But we may have other way to even making it even longer. For example, like fiber join, you can actually join in meter scale. So I would say really depending on some of the application and different technique to fabricate this.
Yeah, thank you. So now Professor Alu.
Yes, thank you, Howard, for the great talk. Very interesting. I wanted to follow up on Aydogan's question about the loss. You are showing this advanced growth for these materials, and still we see that around the plasma frequency, the imaginary part of epsilon is about 1. So many of the applications you showed, probably for this reason, were about absorption or sensing. What I wanted to ask is, would it make more sense to actually work? I mean, I like the aspect of being able to use this for tuning through doping. Would it make more sense to actually work away from the ENZ, but exploiting other ways of impedance matching the material to free space in a way that you actually can rely both on the tunability and on the lower loss than you see at the material resonance? It's just a thought.
Yeah, so yeah, definitely, you're right. So most of the times when we're doing this active modulation, to get this strong modulations, for example, the one I showed in even the matter surface structure or the plasmonic modulator, we're actually dealing with coupling to the ENC resonance, and they are actually quite lossy. So I would say at the moment we haven't been working on that approach yet. So we still actually coupling to the ENC resonance so that you can have a strong confinement to enhancing the field. But definitely, I will agree for sure, 100%. It's like one of the limitations is the losses of the ENC material in some of the applications, particularly for the non-linearity itself. We saw actually if we can enhance the losses, maybe reduce 10 times, 100 times, your non-linear effect could be built up significantly. So that's actually something we are kind of working on as trying to find some low loss ENC material. Other than this TCO, there's some other option as well. For example, polymer, they actually have quite low loss and some other mechanics. So this is something we're also working on. But still, I would say for this TCO material, we still have a decent losses. And again, we are talking about, we are not integrating, for example, for waveguide, we're not integrating for the whole structure, will be just active region with a certain nanoscale dimension, etc.
Okay, thank you. Professor Jagdish, do you have a question?
Thank you, Professor. And Howard, very nice talk and very nice work. And again,
you.
I'll follow up on these things. And in the case of indium tin oxide or so, what is the role of the scattering coming from the non-uniformity or otherwise surface roughness or the interface roughness which you're creating, and also the free carrier absorption losses? Would you like to comment on that and what role they're playing in the performance of your devices?
Yeah, definitely. So certainly we are not a single crystal material that will actually enhance certain losses. And that's why if you try to doing some annealing or some post-processing of the material, actually you can reduce the losses. For example, in our case, our ALD, the good thing is like we're doing with a low temperature deposition. We don't need to do any annealing or high temperature deposition, which is one of the good things, like because you can do it more or less in a room temperature. But at the same time, you don't have the capability to post-processing those. So again, if you really do a high quality fabrication, definitely you can reduce the losses. For example, we have been working on some of the titanium nitride material. And let me just go through this slide. I just quickly mention about, for example, the enhancement of the emission. We're actually using a single crystalline titanium nitride made with in group with Felix Go in Taiwan. And we compare, for example, with the sputtering titanium nitride. So certainly you have lower loss in a single crystal titanium nitride. Actually, your enhancement due to the ENC effect actually much stronger as well. So definitely, if you if you have a better way to making a low loss ENC material, that would be something quite important. But again, I would say ALD is quite decent. We get a quite reasonable losses on this kind of TCO material. And I don't think you can further improve too much from the TCO material, but if you want to go to lower loss material, that would be some other option we are looking at as well.
Okay, thank you.
Okay, thank you.
Professor Yang, yeah. Please unmute your microphone. So I have a short question. Yeah, please.
Okay, Harold, you talk about the angular nonlinearity, and it's a little bit strange because as shown your data, the thin film with a thinner thickness has higher enhancement. Can you explain why?
So it means why the thinner film actually have a higher enhancement?
Yeah.
Yeah, so this actually because of the excitation of the mode. So we actually find the smaller the thickness, actually the higher the enhancement. And actually we find this nonlinearity really related strongly to the field enhancement at the same time your publication of the mode. So then that's one of the reasons we got a much higher nonlinearity. But again, so this is an effective nonlinearity. So doesn't mean that if we make it thicker, you actually get similar nonlinearity. This is for this thickness, we have this effective nonlinearity, and which is normalized to the thickness already. That's why you have a higher nonlinearity. But what that means is that if you want to really making a really small device, let's say 10 nanometer, then this kind of enhancement is quite important because you have a high nonlinearity in a really thin film or even small device structure.
Got it. Thanks a lot for your explanation.
Okay, thanks to the very last questions from the committee and the answers by the Howard. Thank you very much. So we have a very successful. The first one. Let's move to the next speaker is Professor Rios from the University of Maryland. Okay, please share your screen. The title is Reconfigurable Photonics, a phase change for the better.
Okay, hello everyone. Yeah, hi, thank you so much for the introduction. My name is Carlos Rios. I am an assistant professor at the University of Maryland, where I recently created the group of photonic materials and devices. So I'm particularly interested in finding new materials, doing innovations in material science to drive new photonic technologies. And one of those is what I'm going to be talking today, in which I use phase change materials to improve and add some new functionalities to reconfigurable photonics. So I will start by saying what I mean with reconfigurable photonics. So this is, with reconfigurable photonics, I refer to all the different systems that allows us to actively control light and its many properties. And we can do this in different platforms. So what I'm showing here on the left is an on-chip platform in which we can control the polarization, we can control the amplitude, the phase of light. And different ways we do this is by using thermo-optical effects of materials such as silicon, carrier modulation, mechanical displacements, and others. Similarly, in free space, as I'm showing in here, we are also able to control and deflect the beams of light and use them in free space applications. And some ways to do this kind of modulations is also using electro-optical effects, such as in liquid crystals. That is probably the most common ones in spatial light modulators or even TVs. Also using microelectromechanical systems like this one in here, in which you can move these mirrors and deflect the beam in any direction you want. There are so many other effects, but most of the effects I've mentioned in here are volatile, meaning that they require a constant supply of power, and the moment we turn off this power, the state and the information they carry is lost. And with this comes a constant supply of power that in some systems might also mean cooling effects, that we need to cool the system, which comes with an extra energy penalty. So overall, some of these systems are very energy hungry. We are considering slow applications. And with the slow applications, I mean things such as data storage, or like fixed matrices that we want to establish or configure in a chip and do many multiplications, particle trapping, or reconfigurable telecommunication systems in channels that don't move too fast. And for this, I'm going to be showing you that one way to solve all these problems simultaneously is using phase change materials as a non-volatile light modulator. And the rest of my talk is trying to convince you that this is the case. So I'm going to introduce what I mean with phase change materials. I'm talking about chalcogenide alloys that contain one of the chalcogen elements, selenium, sulfur, or tellurium. And these alloys undergo a solid-to-solid transition between the crystalline and amorphous state. And we can do so by, if we have a material initially in crystalline, we can melt, quench it very quickly and bring it to the amorphous. And we can also anneal over the crystallization temperature and bring the material back to crystalline state. Both states are stable, and the fact that they are stable allows us to have non-volatile storage or non-volatile response, because we can codify information in each of them, and it's going to retain the phase for time spanning into decades, as it's been demonstrated before. This control is done with a heat stimuli, but the heat stimuli can come from electrical pulses, from optical pulses, from a microheater in the vicinity of the material. So there is plenty of opportunities when it comes to devices. And in fact, these materials are also heavily studied in electronics. They scale really well to nano. We use films under 30 nanometers usually. Some alloys are very fast, and they're inexpensive, work well at room temperature, and they've been commercially successful because they were used in compact disc technologies, etc. But the most interesting aspect, and we are here all meeting around light, is the large optical contrast. And with this, I mean this kind of behavior. So we are looking at GST, the most well-known phase change material, and on the left side, we're looking at the refractive index, modulation, the black lines, and we see that when we go from amorphous to a crystalline state, the change in refractive index is gigantic, right? For those in optics, you know that in refractive index change of 3 is huge, and it's orders of magnitude larger than many of the other effects that we use to modulate light. But simultaneously, we also have a modulation of the extinction coefficient, which gives accounts of losses. So in this case, the amorphous GST is low loss in the amorphous state, but the moment we bring it to crystalline, it will be very absorptive. So we can think about amplitude modulation. So in the end, it's like having two materials in one, and by just configuring the material, we can change the properties of an optical system. And if we combine all these great properties of phase change materials that I just mentioned, and we put it together with photonics, which we all can agree has a lot of different options and applications, then we get a non-volatile reconfigurable photonics. So it's again the reconfigurable photonics, the act of controlling actively light to different platforms, but this time we will have it stable over time. And when we do so, we have non-volatile behavior that is like that. I want you to remember that it means low energy. we've integrated these phase change materials into many different devices. I'm showing here some of the applications I've been working with in the last years. There are many more, and there are other groups, of course, also working on these with great results, but unfortunately I don't have the time to go through all of those. But here I want to show you how using thin film phase change materials, we can pattern, we can create patterns with incredible resolution, with color depth modulation that could be used as display, color filters, spatial light modulators, etc. At MIT recently, in my years as a postdoc, we work on creating meta surfaces in which the meta atoms were made out of phase change materials, and we embedded these meta atoms on this meta surface on top of micro heaters, and we were able to dynamically control the response of the meta surface with a non-volatile behavior using these materials. We've also used these materials with other platforms such as graphene, looking for a transparent micro heater for applications such as transmissive meta surfaces or like micro heaters that can be integrated to any photonic circuit. But for the rest of my talk, I'm going to be focusing in this aspect, and it's integrating phase change materials to photonic integrated circuits and finding on-chip non-volatile phase or amplitude modulators. So if we start by studying the amplitude modulation properties, we can embed the phase change material, a GST cell, on top of a photonic waveguide. So this is a waveguide on silicon or silicon nitride. And if it's originally in crystalline state, a read pulse will propagate through and see very low light out because a lot of light is lost to the material. And if we send a pump pulse that will write with a lot of power, it can trigger a phase transition and then bring it to amorphous. So therefore, a second read pulse will see a much higher transmission. And we can therefore codify the information in the amplitude. And with this, we actually demonstrated the first on-chip photonic memory nearly 5 to 6 years ago. And with this, we can think about ways to alleviate the Foy-Neumann bottleneck, because having a photonic memory might lead to avoiding electro-optical conversions. So here is some of the experimental results. Not only we got zeros to ones like binary memories, but we also demonstrated that with a mixture, controlling the mixture of material between the crystalline and amorphous, we can have multi-levels. In this case, we are having A levels, a 3-bit memory cell in a single, 3-bit levels in a single memory cell. And this is the experimental demonstration. The black line is light transmission. So this is how much light is propagating through the photonic circuit. And we showed that we can reach any single level in different directions and so on. You might be wondering what multi-level memories are good for. Well, one quick answer is we can do computation directly in memory. And the way we did so, and we demonstrated the first in-memory computing platform in this paper in here, it was by codifying a number to the transmittance function given by the phase change material and a second number to the amplitude of an input pulse. When the pulse propagates through, the output pulse is nothing but the multiplication of these two numbers. And we demonstrated that this scalar multiplication works actually pretty well. Another application we did is we demonstrated the first on-chip optical synapse. And then we did so with a very similar structure, photonic waveguide with different islands of phase change materials. And with this, we demonstrated that we can codify different weights of information in the transmission of light. And this wasn't only devices. After I left my group at Oxford and where I was doing my PhD, they continued to work and they took the phase change synapse and demonstrated the first all-photonic spiky neuron. So they took different synapses and demonstrated the full neuron. Unfortunately, I don't have the time to go to all the details at this point. And also here in a Nature paper that came out this year, they demonstrated the in-memory computing element that I demonstrated before, and they embedded it in a big matrix. So instead of having a scalar multiplication, you're actually now having vector matrix multiplication with a matrix that is codifying in memories and that can only be reconfigured when needed and will save a lot of energy in the long run. So these two demonstrations are architecture level demonstrations that prove that the phase change materials hold a lot of promise in this aspect. However, an all-optical approach is not easily scalable. Here we're talking about configuring each of these phase change materials with a pump probe scheme, but that is really difficult. We want to think about architectures in the hundreds or thousands of devices. Very quickly, I want to mention that when we think about the future of computing, three usually topics are come as solutions, and one is bare memory storage, bi-inspired computing, in-memory computing. And what I've been showing you in the previous slides is that combining absorptive phase change materials with photonics are actually promising candidates for the three of them. So very exciting about this, and looking forward to see a future research will bring us. So now, more recently, I've been interested in researching phase-only modulation. And this is because phase shifters are by far the most important building block for photonic integrated circuits, and we find them everywhere in on-chip technology. So if we see this in this plot here, I am plotting all the different phase change materials. In the horizontal axis, I'm showing the change in refractive index, which tells us about the phase shift. And in the vertical axis, I'm showing the change of the extinction coefficient that tells us about the attenuation. So the GST, the one I used before, gives us a high amplitude modulation, and that's the reason why we were using it from amplitude and analog computing in photonics. But if we want to be talking about phase only, then we need to be sitting in this axis where there is no attenuation and find like the largest phase modulation in here. And to do so, we focus on this element and this alloy called antimony selenide. And if you can see here in the refractive index, both extinction coefficients are 0 around the telecommunication wavelengths, and the change in refractive index is still very large. And with this, we can do phase shifts in silicon uninsulated waveguides of about 0.1 pi per micron, which is actually really good. We did so in this paper that we put on archive recently. We demonstrated the first phase change material-based phase shifter, which is ultra compact with only 6 microns. We did pi/2 phase shift. We can electrically reconfigure it, which solves the scalability problem I mentioned earlier. It's non-volatile, so it's great for like slower sporadic configuration applications. And moreover, we did it with a CMOS processing, which can show some of the future in terms of fabricating these devices. We put this phase shifter in many devices, some of them like MCI switches in here, in which by introducing pi/2 phase shifts, we guided the light either to the red channel or to the black channel. We put it on unbalanced MCIs, and we showed that we can phase shift the interferogram depending on like the design of the phase change material, its sites, etc. We've been able to cycle reversibly up to 250 times. Not that the device broke there, but that's where the experiment was stopped. So showing that we can really reconfigure this device many times. We also added the phase change materials to other structures, such as ring resonators, and demonstrated that we can tune the resonance peaks of these rings, that we can switch reversibly several times. If we add a drop port, for instance, in here, we showed that we can modulate, of course, both. As we modulate the through, the drop is modulated as well. And this is very exciting. We can think about wavelength filtering applications in which, in case the micro ring resonator is not perfectly as expected, or like usually there are fabrication deviations from what we expect, we can come and tune it again with this non-volatile phase shifter. And once we found the wavelength we want to filter, we leave it alone, and without power consumption, the filtering is guaranteed. And talking about this, here I'm showing some unique applications of non-volatility. There are some applications that we don't even need to have reversible switching if we want. And one of those is, for instance, having this odd-drop ring resonator in which the coupling between the ring and the drop port is modulated in time. We modulate and tune these coupling coefficients by putting a phase change material here in the middle, and as shown here in this picture. And these are experimental results in which what we did is we took a ring resonator here in the black line that was originally overcoupled, and we were able to switch it and bring it to the point in which the ring is critically coupled. And once we fine tune the ring resonator to the point we want, we don't really need to keep supplying power to leave it there. Another application on the same line on trimming ring resonators is shown in here. We have 2 different ring resonators. The image is here, connected to a single bus waveguide. And when we measure the transmission, we can see at some points of the spectrum a splitting of 2 peaks. And what we can do is move one of those and make them match. And once we make them match, we are demonstrating that we can successfully trim ring resonators pretty well, which can be a good solution for fabrication issues, and also like even engineering the dispersion within these ring resonators. Another simple but actually very powerful applications is using transient couplers for wafer scale probing. So when a wafer comes out of a foundry, it is really hard to probe locally different photonic integrated circuits as it's done, for instance, in electronics. So one thing that we proposed in this paper was we can use a test port that if we put the phase change materials in amorphous, it takes 5% of the light from the main waveguide. And in this way, we can test if the different photonic circuits are working well. And once we're done with the testing, we anneal the wafer, all the different phase change material becomes crystalline, and therefore no light is longer coupled to the test port. And we demonstrated this experimentally and showed that even in the crystalline state, the insertion losses are 0.02 dB, which is pretty low, and the main waveguide light is still unchanged. So those are some nice applications. Another very important thing of non-volatility is the low energy consumption. In this case, I'm showing a 32 times 32 silicon photonic switch that was demonstrated in this paper using thermo-optical phase shifters. And then they required a 1.9 watts power consumption, whereas if we were to do the same with phase change materials, we would need only 10.8 milliwatts. So if we start comparing and thinking about, okay, what if we reconfigure every 1 millisecond? Okay, at that point, the energy, the thermo-optical phase shifter outperforms phase change materials. But if the reconfiguration is slower and slower in different applications that might require this, we see how quickly, because the phase change material is non-volatile, the energy is the same, whereas the thermo-optical phase shifter have a constant supply of energy, start increasing really fast. And after a minute, we are already 4 orders of magnitude lower energy. So this is the kind of energy saving that I'm talking about. So moving forward, there are a lot of things that can be done in different aspects from a material point of view, a device point of view, and applications. And my research is transversal to these 3 different topics. In materials, we can still focus a lot on finding and expanding the optical phase change materials library, finding new alloys that are particularly and specifically tailored for certain applications, and find some that can be switched faster depending on the application. Of course, lower melting temperature will lead to lower switching power. Understand the failure mechanisms is really important because this will eventually help us improve the cyclability and bring this technology to the next level. At the device level, there is, of course, many different things, many proof of concepts. Phase change materials can be integrated to any different photonic application, really. So this is transversal to any photonic application. It's a building block that can be used in many different areas. So we can think about integrating them with other photonic structures and like plasmonics and etc. Think about large PCM switching if we want to make like large metal surfaces applications. And one that is very interesting for me is really moving towards integrating these materials in CMOS photonic boundaries, because only then it will become accessible for everyone. The application level, there is, of course, a lot of things to be done. I mentioned that we can build a phase shifter, and phase shifters are everywhere in integrated photonics. So the application, really, you name it. We can think about photonic networks, quantum processing, even LiDAR for the applications in which you need to steer the beam slowly. Of course, neuromorphic computing and adaptive optics in free space with the meta surfaces. So this field is growing really fast. In around 2013, we published the first papers on the topic, and it's been growing really fast. This is still very new, so there is plenty of opportunities ahead, and very much looking forward to all that exciting things that are going to come in the future. Here, I want to thank all my mentors and all the labs I've been working throughout my career, and thanks to whom I am all here from the University of Antioquia in Colombia, where I did my undergrad, all the way to MIT, where I recently did my postdoc, Oxford, where I did my PhD, and with Professor Wolfram Pernis when he was at Karlsruhe, where I did my master's. So thank you to all of them. And I want to leave you with these conclusive remarks here. And as a take-home message, I want you to keep in mind that what I've shown you, it's a new building block for photonic integrated circuits, but we've done it in any other application that can allow non-volatile reconfiguration, so low energy consumption. The large optical properties means small form factors, and they are scalable. And if we use lossy phase change materials, we have amplitude modulation, And if we use transparent, we can have phase shift. And with this, I want to thank you all for your attention and happy to take any questions.
Okay, thank you, Professor Rios. You keep the time very successful. So now the session is open for question. Yeah, Professor Yang, please.
Yeah, thanks for giving us, showing us the wonderful future of phase-changing materials. I believe in that. I am particularly interested in your experiments on waveguide coupled resonator. You use this material to modulate either the frequency, help to change the coupling coefficient, right? Or help to bring two different resonator to be on resonance simultaneously. But I have a question. When you use that to tune the coupling coefficient, I notice resonance also change. Can you do one thing at a time? Say, for example, in some case, I only want to change the coupling coefficient without changing the resonance frequency. Is it possible to achieve that?
That's a very good question. So we haven't done that. The reason why there is extinction, the extinction ratio modulation comes from the modulation of the coupling coefficients. But at the same time, the material is on top of the ring resonator, and therefore there is also phase shift. So that's why both are moving. We are planning on running more experiments in which, for instance, the phase change material can only be on the drop waveguide instead of also sitting on top of the ring. And I think by doing so, we will avoid the phase shift. That means the frequency tuning of the ring resonator, but still we will be modulating the coupling coefficient. So I guess my answer is yes, that is possible. It requires more engineering and more design of the system, but yeah, we are going to actually try that in the near future.
Okay, that'd be great. Look forward to your update in the future. Thanks.
Perfect. I'll let you know. Thank you very much.
Yeah, thank you. Professor Alu, you raise your hand. Your question, please.
Yes, thank you. I also enjoyed your talk.
Thank you very much.
I wanted to ask you, for the transparent PCMs, I was very interested in your results on phase shifters and potential opportunities even for arrays and metasurfaces. I wanted to know, what is the residual loss that you observe in this setup, and how can you compare it with other competing technologies?
Yeah, absolutely. So I didn't put the figures in here, but the insertion loss of our phase shifter is 0.3 dBs. And for this small phase shifter, which is pretty good and comparable with other technologies, and I have to tell you that most of that loss actually comes from the dope silicon. We're using dope silicon as a microheater. So we are now working on re-engineering the microheater and see if we can compensate with geometry a lower doping concentration, because then we can even drive the losses even lower. There is also an excess loss when we switch of only 0.011 dB per micron, which is very small as well. And that's mostly due to the scattering effects that are unavoidable or when we put this phase change material on top. But both of them are losses that we can engineer properly to reduce. And that's, again, another direction in which we are moving. But we are very happy that even with this proof of concept, we are already in such a small insertion loss is comparable with the thermo-optical phase shifters.
Yeah.
Thank you.
Professor Oskan.
Thanks for this presentation. So I had a question. In one of your slides, you were mentioning an application where you had this phase change material to probe some of the integrated photonic circuits by drawing 5% and then changing. So obviously, this disadvantage that I can see that is that you're using some of your landscape to do that probing. What is the advantage here for that kind of an application compared to a near field probe doing the same kind of testing that you want to do, but without actually fabricating anything or without wasting the space with something that you won't use in the future? Just curious.
Yeah, absolutely. So I think one of the biggest advantages is that we can tap the actual mode propagating into waveguides. We can engineer to tap any power we want. And when we are like doing so, we have a really good signal to noise ratio. We can test our devices in a very with a pretty good clarity in the results and what the circuits are showing. I'm not so familiar with the near field techniques. I've seen other techniques in which they make, for instance, gratings, doping silicon locally, and then similarly you anneal and the doping it's gone. But again, that is very complicated. You need like ion implantation and so on. So I agree. This method that we propose takes real state of the chip, which means a lot of money. But if we're thinking about probes or test ports that are not like everywhere, but just in very specific and strategical points, I don't see how it could be a disadvantage. And yeah, the fact that we can tap the actual modes propagated in the waveguides and the high intensity that we can take from there, I think it's an advantage. In that paper, we show how we can tap and get like a very good behavior of a ring resonator, for instance, and then completely turn it off. So I think that makes it a very interesting technology to have a look at. Thanks for the question.
Thanks.
Yeah, so question, please.
Yeah. Can I ask a question?
Sure.
Yeah. Okay, Min, go ahead. You have been waiting for quite some time.
Yeah, I have a question about the phase modulation. You started several different type of PCMs, which is a great work. But what about the modulation speed? We have been also studied these materials, but the problem is sometimes it's very slow to modulate it. And what's your experience on that? And is it possible to get a very high speed modulation by choosing different or one type of PCM?
Yeah, that's a very good question. And the different phase change materials come with different switching speeds because that comes with the intrinsic properties of the phase transition. So the ones we were using for photonic computing, GST, that's one of the fastest ones that we use. It switches in nanosecond timescales. But when I get this question, I always say, okay, yes, you will switch in megahertz in this technology, in this phase shifter that I show you. Let's say like fully reliable, you do 1 kilohertz, which is very slow, but we are not planning on like overtaking doped silicon electro-optical modulation, right? Like in the really fast domain of photonics, there is a lot of really great work. And what we really want this technology to be used is in the other extreme, which we have slow configuration. Not all the applications are fast, but if we use fast modulation in slow applications, we're wasting a lot of energy. And that's the problem we want to tackle. We want to use the non-volatility of this material to completely create a new family of applications on the other side. We are not looking to replace the very fast modulations because there are better materials and better platforms by far. So yes, they are slow, but for the applications we're proposing, they are perfect.
Okay.
Okay, thank you. Professor Jagdish?
Yeah, sure. Thank you. Carlos, very nice work and beautiful talk. And so the SPAC is a very challenging material. And I was wondering that particularly the defects and interfaces and other things and what role they play in terms of the performance of your phase shifters.
So that's a very good question. We haven't seen much effect quite yet. It's actually the way we fabricate these devices is extremely easy. That's another advantage of this mechanism. So we basically thermo-evaporated, and in a lift-off process, we have the material on top of the waveguide. The interface with silicon waveguides and with silicon nitride waveguides have not been a problem. And since we're tackling mostly optical interaction, I think maybe some of these defects won't have that much issues or won't have such a big impact. But to be honest, that's still an open question. That's a work that we've done in the last month. We still need to work a lot in understanding the failure mechanisms because when we drive optically, we've seen that we can switch many thousands of millions of times, but when we're switching electrothermally, it's a more violent process and the materials start failing at hundreds of times. And to understand those failures, I think we have to go to like the pure material science aspects and start asking ourselves, okay, these defects, are they being a problem? How can we solve these? So that's why I say that on the material aspect of my research, one of the open questions is, what are the failure mechanisms? We need to understand them well in order to show that this is robust and we can actually get the cyclability we want for this to be a viable technology.
Okay, thank you.
Thank you very much.
Okay, very nice talk and very nice questions. Thanks to Carlos and thanks to the committee. So let's move to the next.
Thank you very much.
The next speaker is Professor McMahon from Cornell University. The title is the Computing with Light. Share your screen. Yeah, it's perfect. So Peter, please.
Excellent. Thank you very much. So first of all, I'd like to thank the panel for the opportunity to tell you a little bit about our work. Today, I'm going to tell you about a subset of what my lab at Cornell has been working on. We broadly speaking work on the physics of computation. And today I will tell you about our efforts to perform computing with light, in particular focused on neural networks. So before I dive into the technical material, I'd like to acknowledge the members of my group. These are the people who, of course, are doing the actual work, and I'm really here to do the advertising. And I'd also like to acknowledge the funding agents who funded the particular work that I'm going to talk about today, which is NTT and the NSF. So I'm going to tell you about two stories today. The first is on constructing optical neural networks using linear optics, as well as optical neural networks using nonlinear optics. But to set the stage for that, I'll describe very briefly what we intend to do with optics related to neural networks and how that will help neural network processing. And in both stories, the motivation will be the same. It will essentially be, how can we improve the energy efficiency of the inference mode in neural networks? So to dive in, just to make sure that we're all on the same page about what our goal is, I will quickly remind everyone about inference versus training in machine learning. So in machine learning, we have typically two phases, and the inference phase, we are, for example, given some image of a handwritten digit, and we are going to send that into a machine learning model and ask it to make a prediction of what the image is. In this case, it's an 8. So in inference, you're given a trained model and some new piece of data, and you ask the model to make a prediction for you. In the training phase, you are given some large data set of labeled data, for example, many examples of 0 and saying these are all 0 and so on. And the goal is, given this labeled data set, produce a trained model that is then in the inference phase used to make predictions on new data. And the reason that I'm bringing this up is that the work that I'm going to tell you about today is focused on improving energy efficiency on the inference phase, not on the training phase. Even though that's also an important problem, we're focusing on inference. Why is it reasonable to just focus on inference? Well, it turns out that in many applications in machine learning, the inference costs can dominate. They can be somewhere between 80 and 90% of the total costs. And this is a statement that's been made by a number of organizations, including Amazon and NVIDIA and McKinsey. And the fundamental motivation for this is that in many cases, you have a few engineers developing a machine learning model that they train it. And then once it is trained, admittedly on a large data set, that model is deployed to the cloud where it is used by hundreds of thousands or perhaps even millions of users in inference mode. And so that is why inference costs in some applications can dominate. So again, for focusing on inference, the goal we're aiming for is to be able to take pieces of data and make predictions about them. And in the most simple kind of canonical form of a neural network, you may have a structure like this, where we have some input layer, we have an output layer, and the input layer we feed in, for example, our image, where each pixel gets mapped to, for example, a single neuron. And then the mathematical structure that underlies a basic neural network like this, this so-called multi-layer perceptron, is that we propagate the information from layer to layer with matrix vector multiplications. So we can think of each layer of neurons as being represented by a vector, and to propagate from one layer to the next, you multiply by a matrix that encodes the weights of these connections that you see here between neurons. And then once the matrix vector multiplication has taken place, you apply an element-wise nonlinearity at each neuron before you proceed to the next layer. And then you repeat this with the matrix vector multiplication for the next layer and so on. So if you're going to build a hardware accelerator for inference, there are essentially two options you have. You can either try to make something with an exact mathematical equivalence versus this with respect to this mathematical structure that I showed here, or you can have something that has just an approximate mathematical equivalence. So if you make one with an exact mathematical equivalence, the advantage of that is that any model that you train on, for example, a CPU or a GPU or a TPU or any other kind of conventional CMOS processor, you can use that model directly as is on your hardware, because your hardware, your photonic hardware, does exactly the same mathematical operations as the CPU does. The disadvantage of building an accelerator with an exact equivalence is that now you need to very carefully engineer it so that you have this equivalence, and that means you can leave some energy efficiency on the table. Alternatively, you can build an accelerator that has just an approximate equivalence with this mathematical structure. And the advantage of this is that you can make the hardware more energy efficient, but the disadvantage is now that the models you've trained on your CPU may need to be retrained or at least modified a little bit because there is not an exact equivalence anymore. Something that's worth pointing out is that although I've said approximate equivalence here because it makes for a nice duality between these two, you don't even really need it to be approximate in the sense of close to the mathematics. You just need the mathematical structure to be sort of vaguely inspired by the one that's shown here. And we and others have shown that even this sort of vague inspiration from this structure can still be made to work. So why would you use optics to build a neural network accelerator of either kind, one with an exact or an approximate equivalence to the mathematical structure? There are several reasons. This is not an exhaustive list, but 4 reasons that I like that are at least somewhat relevant in the work that I'll show you today are these ones here of bandwidth, spatial parallelism, dissipationless dynamics, and wave physics. So in the case of bandwidths, one of the things that you can imagine taking advantage of in optics is that optical pulses can have a bandwidth that's up to 100,000 times larger than in electronics. So you can have, for example, 500 terahertz of bandwidth versus 5 gigahertz of bandwidth in electronics. There's also a large amount of spatial parallelism that you can exploit in optics, and we all know this very well now from our cell phones alone have cameras and displays that have millions of pixels. A very important feature of optics is that you can have nearly dissipationless dynamics, that as you propagate light through an optical setup, especially in free space, but even in some on-chip settings, the light can propagate with almost no loss, and through its propagation can have computations being performed. For example, if you put light through a lens performs a Fourier transform for you. And then finally, wave physics is also something that is an interesting feature of light, where we can, in everyday life, you can see wave phenomena from individual photons or collections of photons, whereas exploiting the wave nature of individual electrons is very difficult. So with that somewhat sort of generic overview of features of optics that you might try to take advantage of, I'm now going to show you 2 concrete pieces of work where we've, in different ways and different combinations, exploited these potential advantages or features. So in this first work, I'm going to describe how we've been able to construct optical neural networks using linear optics. And our main target in this was to show that we can perform optical neural network processing with extremely low light levels, extremely low amounts of optical power, which suggests that the potential for energy efficiency. So the main building block in this is we're going to be building a neural network that has an exact equivalence with the conventional model of a neural network. And to do this, we're going to use an optical matrix vector multiplier. So there's been a lot of interesting work in this field over the last few years. This is an example from Dirk England's group at MIT, but in Carlos's very nice talk just before mine, you also saw some examples of this. So you can build devices on chip that can perform matrix vector multiplications for you. Alternatively, you can work in free space. And this is not a new idea. This goes back to at least the 1970s to Goodman, but arguably even before. And you can imagine constructing matrix vector multiplications that happen where you have some input of your vector, for example, from an array of LEDs or VCSELs. This is expanded and fanned out using a cylindrical lens to a spatial light modulator that encodes the matrix that you would like to multiply by. This performs element-wise multiplications at each pixel, and then the resulting outputs are summed using another lens that collapses this matrix down to a vector again. And these are just two examples. There are many others that people have been working on. So a question you might ask with this is, how many photons do you need for this to work? So this scheme that's shown at the bottom here is the scheme that we will be implementing, but it's very similar to the Goodman scheme from this previous slide here. And essentially, our setting is that we will have our vector being encoded in a square rather than a line, a fan out that works in this way of each of the colors represents a different vector. We're going to use the same wavelength of light. The color here is purely intended as a kind of an aid to follow what's going on. And once the fan out has happened, the light propagates through a spatial light modulator encoding the matrix. And then we perform collapses using lenses that will collapse or sum modes of light to individual detectors. And each of these detectors will represent an element of the output vector. And the question you can ask is, how many photons do you need? And what you would intuitively like is that each detector detects many photons so that it gets an answer with a reasonably high accuracy from signal to noise. And the way you can achieve this is if you have many spatial modes going into each lens that have less than a photon on average per spatial mode, if you have many of them that are summed at the detector, then you can still have a large number of photons at the detector, even though each individual mode had a small number of average photons. And this is something that was pointed out in a couple of theory papers fairly recently. And the main message is that you can achieve subphoton per multiplication energy efficiency if your vector size is large enough. And so we have set out to try show that this works in practice. So we constructed an optical setup with the explicit goal of trying to carefully show this point. We did it with an OLED display and a single detector here, shown here with an SLM in between to encode. In our first demonstrations, we did vector-vector dot products and then expanded to matrix vector products. So you encode one vector on the display, one vector on the SLM, and then you look at the output, which should be in a dot product, a single scalar. This is the optical setup in our lab. And the experiment that we performed was characterizing the accuracy of the output of the vector-vector dot product, which is shown in the RMS error in the y-axis here, as a function of how many photons we allowed ourselves to use during the multiplication. So basically by modulating the intensity of the light source. And what we can see is something very interesting, is that even when we have a thousandth of a photon on average per multiplication, which is all the way on the left side of the graph here, the error that we have is only 6%. And as you increase the amount of power that you use, that's the number of photons per multiplication, you can see that the error decreases as you would expect. But perhaps the most important point is that these numbers are very reasonable. Once you get to 1 photon per multiplication, you're very much sub 1% error. This happened in the case of a very large vector size, n equals 500,000 or slightly larger than that. And if you have a smaller vector size, then the error increases, which is something that you would expect. An important caveat on energy consumption here is that although this shows that extremely low optical powers are needed to get good accuracy, if you're thinking about the overall system efficiency, we still use a large amount of power relative to a digital processor because the optical to electronic and electronic to optical conversions are not very efficient. And this really suggests the need to improve energy efficiency in conversion in converters. And this was a point that was also made in both of these theory papers. One interesting side note is that if you remove the optical electronic conversion at one of the stages, for example, by directly taking optical input, you can get rid of at least one of the conversion stages in the first layer of a network. But nevertheless, it's an important challenge for the field. So what is such a vector-vector dot product engine or matrix vector multiplication engine good for? Of course, as we motivated at the start of this talk, you can try to do neural network processing using this as a building block, where neural networks are robust to noise. So in inference mode, you can get away with low precision. And so there's a very good match between optical analog matrix vector multipliers and neural network processing. And this has really been brought to the forefront by a series of really nice papers from different groups over the past few years. For example, this work from MIT, UCLA, and Tsinghua. And there's a nice review showing some of the history of this going back to the 1980s. So we've now done our own demonstration of this with our system, where we did MNIST handwritten digit processing, where the matrix vector multiplications were done optically, but the nonlinearity was applied in electronics. And our key result is shown here is that the accuracy of MNIST handwritten digit classification as a function of the amount of power we use, the most important point is this one here, showing that with less than a photon per scalar multiplication, we can still achieve 90% accuracy in MNIST. So that's an attempt with linear optics. As was suggested, though, you would like to perform nonlinearity in the optical system too, and not just in electronics. And so this is the second piece of work that I'll quickly show you, is our attempt to try and harness nonlinearity in optical frequency conversion process to perform neural network processing. And again, the goal is to perform inference efficiently. We would like to do something sort of channeling the motivation of Feynman in quantum computing of, in a classical system that's difficult to simulate, can we exploit the complex behavior that the classical system shows? We all know many classical systems can be difficult to simulate, but easy to sort of see in a real setting. This is showing fluid flow over a car, but you can imagine similar things in optics being difficult to simulate. And we would like to try and sort of turn that situation around and harness it. The challenge, though, is how do you take some arbitrary physical system, including optical systems, and make them behave as a neural network? Because it's a nice intuition that you should somehow be able to harness their complex dynamics, but how do you actually do it? And so this is the challenge that we set out to solve. And to give some sort of flavor for how we can think about physical systems acting as a neural network, if we think of a kind of conventional feed-forward neural network where we send in an image 8 and we ask it to classify that this is an 8, the multi-layer nature of a standard artificial neural network that I showed earlier can be represented in this way. There are a series of layers that the information propagates through, where each layer there are some set of parameters. And the typical thing that one does in an artificial neural network is, for example, have matrix multiplication and element-wise nonlinearity in each of these blocks, or maybe some convolutional layers. But our motivation, or our kind of hypothesis, was that why does it have to be this way? What you can instead do is put a physical system into each of these blocks and control some parameters of the physical system. And the physical system, when you send some input and parameters to it, it will evolve under its natural dynamics and give you an output. So it will give you some nonlinear input-output map that you can control with parameters. And you can use this as your building block instead. And it doesn't have to be optics. It could be mechanics, it could be electronics, it could be anything. So we wanted to try to do that. Here's an example of something we constructed to do, in this case, vowel recognition as our task, with a 5-layer neural network where each layer is implemented by a nonlinear optical setup, where we have a laser that is pulsed, so it has some broad spectrum. We pass it through a pulse shaper that we use to encode both the data as well as the parameters. And then this gets passed through a nonlinear crystal where a second harmonic generation process takes place. And then we measure the output of this on a spectrometer. And that's the input-output map. We essentially have an input spectrum and an output spectrum that has undergone some nonlinear processing in this crystal. And at each stage, we will use a different set of parameters so that we are controlling the transformation that happens in the multi-layer neural network. We devised a procedure to be able to train a system to do this, because it's not so kind of clear a priori how you would now choose your parameters. How do you pick the parameters such that this works? And our kind of key concepts are that we will use differentiable digital models, and we will also involve the hardware in the training process so that you don't get a divergence from what your model believes is happening and what the physical system is actually doing. And this shows some results for the Bower classification. Here's classification accuracy as a function of the training epoch. And what we can see in the blue curve is that our system is able to achieve a 93% accuracy using our training method. The black curve here is showing that if you only use a kind of naive training method of in silico, that it doesn't work. But if you use this method that we developed, where you have hardware in the loop, then you can make this kind of scheme work. We did this with a number of different hardware platforms. And in this case, now I'm going to show you for handwritten digit classification, so a slightly different and more difficult task. We can see that with a mechanical system with a metal plate attached to a speaker, so something that at first glance you would think has no hope of being able to do handwritten digit classification, we can actually get about 90% accuracy. We also did it with a very simple RLC circuit with a transistor in it to add nonlinearity, and again can get above 90% with a slightly different machine learning architecture. And then our nonlinear optical setup on this task of handwritten digit classification was able to achieve 97% accuracy. Now that we've shown this, we're very interested in looking at other physical systems, including in optics, for how we could try and harness them to perform neural network processing. We've made available our code so that anyone who would like to try this on their own is able to, but we're also happy to answer questions about it. And with that, I'll leave you up a summary of what I've discussed today. We've developed hardware accelerators for neural networks that have an exact equivalence with conventional machine learning neural network models. And we use linear optics in this case to perform matrix vector multiplications. And then in the second part, I showed you how we could harness nonlinear optics in a way that is sort of more inspired by the structure of neural networks than having an even approximate connection with the mathematical structure that you conventionally see. So thank you very much for your attention, and I'll be happy to take any questions.
Okay, thank you. Very nice networks with linear optics and nonlinear optics. So now the session is open for question.
So can I ask a question,
Professor Cao, please. Professor Cao. Yeah.
Hi. Hi, Peter. Great work. So I have a question. So in the first part, you talk about linear optics, which is really energy efficient. The second part, you're using nonlinear optics, give you much more functionality. So how about the energy efficiency for the nonlinear, using nonlinear optics? How much power do you need to do that? Is there any way to combine these two?
Right, that's a great question. So I think there are essentially two parts to that question. One is, what is the energy efficiency situation when you are using nonlinear optics? Mm-hmm. And also, you hinted at something that's very important, is that in a neural network, you typically want some linear part as well as some nonlinear part. You don't only want a nonlinear part. Mm-hmm. And to deal with the energy efficiency question first, I think the intuitive way to think that we think about it is, if you simulate, for example, the nonlinear Schrodinger equation of pulse propagation through a nonlinear fiber, it can take your laptop sort of half an hour or an hour to simulate something that in the lab can happen in literally with 1 picosecond pulse going through a nonlinear fiber in the space of less than a nanosecond, and with not a lot of energy. We think in optics terms, nonlinear optics is expensive in energy, but really when you think about how much energy in a single pulse going through a nonlinear fiber generates complex dynamics, this can be well sort of sub-nanojoule even. So the energy efficiency is in principle there in nonlinear optics. And it's a matter then of how well does that map to the neural network task you're trying to do? Because if your neural network task's goal was to simulate the behavior of a nonlinear pulse, of a pulse propagating through a nonlinear fiber, then you would have a perfect matching, and every operation that the pulse does in the physical system would exactly match and would be perfectly useful to you. And then if you try to make it do MNIST handwritten digit classification, how much overhead is there for you trying to make it do something it doesn't naturally do? And I think we don't have a complete answer on kind of the latter part. We know from the former that there must be some tasks where there's a large energy benefit. There's a kind of existence point of the exact mapping case. But when you start going to more complex, sort of more abstract machine learning tasks, it's essentially an open question for the field. In which situations will you get overall an energy benefit? On the question of kind of linear versus nonlinear processing, I think there are some nonlinear optical systems where you naturally also have some linear propagation that happens in addition to the nonlinearity that happens. So you can kind of naturally have them together. Another option is that you can try and combine things like the two systems that I showed you in the two parts of this talk, where you have some explicitly linear part and then some explicitly nonlinear optical part. And our training procedure is able to train multi-layer neural networks that include both. So that's an interesting direction that we're pursuing at the moment.
Okay, thank you. Question, please. Professor Oscar.
I have a follow-up question. Very nice presentation. So in your forward model, how do you take into account all the higher order terms of your physical nonlinear system? There are some interesting reports that sometimes those higher order unknown unknowns are helping with the model for at least reservoir computing for non-trainable systems. I'm curious, in the example that you showed in part 2, in the forward model, was there any simulation that took into account various different higher order terms, or you don't care about that? You treat it as an experimental system that you have to do some sort of learning in situ?
I see it. That's a great question. So when we started this, what we thought we could do is take standard equations from a nonlinear optics textbook and write a simulation code, and that would simulate the experiment sufficiently accurately that we could then train it and make it work and get correct results. What we found in the case of the nonlinear optical systems, though, is that in many of them, especially, for example, nonlinear fiber propagation, but even thin crystal propagation, you indeed find that getting an exact matching between your theory or simulations and the actual data you get in the lab because of these sort of higher order contributions is not at all easy. And so what we actually did for our model when we are training, our model here, we could have made that a simulation code of nonlinear pulse propagation, for example, but we actually used another machine learning model for that, leveraging the work that's been happening in the community over the last 5 years of using neural network models themselves to model the behavior of nonlinear optics experiments, because those neural network models can then capture the higher order terms and the other non-idealities in the experiment. So that's how we dealt with that. And essentially the kind of in the framework of thinking about this as a machine learning tool, this is something where you need to train this model on your system once, and then you can use it so long as your system doesn't change.
Thank you.
Okay, thank you. Chaoyang, please, question, please.
Oh, yeah. So actually, I have two questions. The first one is, how about the loss in the spatial light modulate you use, and how it will affect, if in the future you would like to scale up the system to larger and larger ones. And the second question is, so 0.00006 photons per weight multiplication, does this sound a little counterintuitive? Is there any physical limit on like how many photons in principle, if everything is perfect, nearly no loss, what is the limit? And if it is counterintuitive, can you offer an intuitive physical picture on how we might be able to more clearly and understand it. Thank you.
Sure, great. Thanks for the questions. So on the first question about loss, I think we're maybe getting near the end of the time. So I'll just quickly say on loss, the propagation loss through our setup was something I want to say like 10%. So it's not extremely high, but also not extremely low. And this can be improved to the extent that you can imagine free space optics having reasonably low loss. So we were using standard commercial components of the lenses as well as the spatial light modulator in reflection mode. Incidentally, when we were computing our less than 1 photon per multiplication, we were taking into account the losses that happened between, like, where the computation was taking place. So it wasn't like we were actually putting in 10 times more photons than that and not counting them. On the second question, the kind of more conceptual question of how is this even possible, it indeed sounds kind of counterintuitive that how can you have a scalar multiplication that takes place where you use less than 1 photon to do it, because how can you even encode the information about either of the vector elements in less than 1 photon? And the kind of key insight there is that this only works if you're trying to do something like vector-vector dot products, where you are summing the contribution of many scalar products. And you cannot do this with just a single scalar multiplication. You have to be doing it where you sum over many of them, and then you basically go to kind of your standard error summing situation of your signal to noise ratio. If you sum over 500,000 terms, if each of them are independently very noisy, if you sum over 500,000, now the overall result is not so noisy. Another way we think about it is that we demonstrated using 1/1000th of a photon per scalar multiplication, but we did it for a vector size of 500,000. So there's actually 500,000, like on the order of 500,000 times by 0.001 photons in the system. So the total number of photons that hit the detector is still kind of in the sort of hundreds to the thousands. So the SNR can still be reasonable, even though each individual scalar multiplication that comprise the vector-vector dot product is very small.
Okay, thank you. The optical computing is very perspective. Thank you very much.
Thank you very much.
Yeah, thanks to the question from the committee. So let's move to the next. Dr. Kai Wang from Stanford University. The title is Multidimensional Photonics on Synthetic Platforms. Kai, please share your screen.
We know.
Oh, can you try again?
Try again. I think there's some problem with my Zoom.
Mm-hmm. Okay, it's fine. Go ahead.
Can you hear me?
Sure, go ahead.
Yeah. All right. Hi, everyone. My name is Kai. I'm currently a postdoc at Stanford University in a group of Professor Xianghui Fan. My talk is about multidimensional photonics on synthetic platforms. So the works in this talk were mainly done at Stanford University and the Australian National University. So photonic systems are prominent for various information processing tasks, from classical to quantum regimes. However, with the processed information capacity going higher and higher, the scalability of such systems becomes a very challenging issue. So both the size of the system and the number of control signals will soon become too large. Therefore, we would ideally want to develop new approaches to better use each and every element in photonic systems. And my solution to this problem is by implementing multidimensional structures in lower dimensional systems. And I want to say that there's plenty of space in higher dimensions. And for this, I use 3 main approaches. So the first approach makes use of the intrinsic degrees of freedom of light, such as polarization or frequency to implement extra dimensions. And second, we can harness the so-called isospectral transformations that preserve the spectrum to map a multi-dimensional network to a low-dimensional system. And the third approach that I will briefly talk about is the use of non-classical property for multiple photons, which can also span a multi-dimensional space with the size exponentially growing with the photon number. Now I will start from the first approach. So the use of intrinsic degrees of freedom of light to form extra dimensions is a rapidly developing research topic in photonics, known as synthetic dimensions. Such systems have been shown a very powerful platform for demonstrating various effects in especially topological photonics. So let me explain the example of a very simple synthetic frequency dimension. So for a ring resonator, we can use the set of frequency modes, eigenmodes, separated by the free spectral range to form a synthetic dimension. And we can use a phase modulation at the FSR to implement couplings between nearest neighbor frequency modes. And long-range couplings can be added by modulating at multiples of FSR. And the coupling strength, range, and phase can all be independently controlled by varying the modulation waveform, which is in sharp contrast to lattices in real space that are subject to many restrictions. So far, most of the synthetic dimension works focused on Hermitian Hamiltonians. For example, if we zoom into two frequency modes, the couplings in one direction is the complex conjugate of the other. This is a Hermitian coupling that ensures energy conservation in this coupling process. But in practice, nearly all physical systems are non-conservative systems. It's therefore highly desirable to bring the flexibility of synthetic dimension to non-Hermitian region. In fact, non-Hermitian periodic systems have very rich and unique topological features, even in one dimension for a single energy band. So the main difference between a Hermitian and a non-Hermitian band structure is that non-Hermitian systems can have complex valued band energies. So we can compare a 1D Hermitian model to a simplest non-Hermitian model known as the Hartano-Nelson model with directional coupling. So if we do a parametric plot in the complex energy space by sweeping the momentum K, you would immediately see that the non-Hermitian system's band energy can form non-trivial loops in the complex energy plane, which are impossible for Hermitian systems. Therefore, as a unique feature to non-Hermitian systems, even only using the eigenvalue of its band energy, band structure, it's already possible to define a topological invariant. This is in sharp contrast to Hermitian systems, where the topological invariants have to be defined through the eigenvectors. One important class of eigenvalue topology is the so-called point gap topology. And this is characterized by a winding number with respect to a certain chosen reference energy. So it basically measures how many times the band winds around the reference energy. Such a winding number has a physical consequence known as non-Hermitian skin effect. So if you truncate the infinite lattice by a one-sided boundary, which is called semi-infinite boundary condition, the eigenspectrum would fill up the entire interior of the loop where the winding number is non-zero. And the eigenstates then becomes localized. So the fold of degeneracy of each localized state is equal to the winding number. So while there are experiments probing the non-Hermitian skin effect, it remained an open question if one can observe its topological underpinnings, which is the winding of the complex energy band itself. So for this purpose, we implemented the Hartano-Nelson model in a synthetic frequency dimension using a dynamically modulated fiber ring resonator. So the Hermitian part of the coupling is implemented by performing a phase modulation similar to what I just mentioned. And the anti-Hermitian part of the coupling that describe the energy non-conservative nature is implemented by an amplitude modulation. So in other words, amplitude modulation here introduces the desired non-chromaticity. And we performed a band structure measurement in such a system and obtained the winding loop as predicted. So the flexibility of the synthetic dimension also allows us to arbitrarily generate complex winding loops. Here we show two experimental examples that we measured with complex windings. So what we showed just now were all within one single energy band. So with more bands, the topology is even richer. For example, with two bands as sketched here, if we plot the band structure as a 3D plot in the space of real part and imaginary part of the energy E and the momentum K, then you will find that the two bands braid around each other. And here it braids twice around each other. And it can be denoted by such a braid diagram. So since 0 and 2 pi correspond to the same momentum, we can close the braid. And this will give rise to a knot or link. So in this example, we have so-called Hopf link. For two non-Hermitian energy bands, depending on the Hamiltonian parameters, they can wind different braid different times around each other and end up with different braids, and their closure would form various knots and links. So actually, it has been shown theoretically that inseparable non-Hermitian bands in one dimension can be classified by the braid group Bn. Here is also a 3-band example that forms the figure 8 knot. So the braid group has a very rich set of topology, richer than many other topological invariants, such as the well-known Chen number that is an integer invariant. In particular, starting from n equals to 3, the braid group becomes non-abelian. Therefore, it's of great fundamental interest to demonstrate such a braid group topology. To do so, we developed a lattice model that can achieve any element in the 2-band braid group. And on the synthetic frequency dimension platform, we implemented such a model using 2 coupled ring resonators. One of them undergoes dynamic modulations in both phase and amplitude. We realized a wide range of 2-band braids in such a non-Hermitian system. For example, here we show 2 examples that braid twice and 3 times. And this serves as the first experimental demonstration of braid group topology in non-Hermitian systems. And we anticipate that such a demonstration will open up a new pathway towards a class of intricate topological behaviors in non-conservative systems. For more information, you could check out this paper that published 2 days ago in Nature. So far, what I showed you were based on electro-optic modulators. And I also worked on implementing synthetic dimension, all optically mediated by third-order nonlinearity in an optical fiber by shaping the optical pump profile. And this can allow a larger spectral spacing between the frequency sites to tens or even hundreds of gigahertz. And this is particularly interesting for future developments of such systems into integrated micro-ring resonators that have larger FSR. So on such an all-optical platform, we experimentally demonstrated 2 applications. One is to implement a 1D frequency lattice that with a few orders of coupling, and we mapped the coupling orders to multiple dimensions, and this gives rise to a chiral tube lattice, and there is non-trivial gauge field. And in another work, we utilized such a synthetic frequency lattice for a single shot reconstruction of frequency clumps. So the synthetic lattice spreads out the input of a few discrete frequencies, so into more frequencies. And then only by performing the intensity measurement at the output, we can fully extract the input frequency clump in not only the amplitude, but also phase and coherence. And to summarize a bit here, we have shown a very rich set of topologies with complex winding loops or braids or knots. But in fact, these were just using one or two optical ring resonators without actual spatial dimensions. So due to the use of frequency modes as well as non-chromaticity. So non-Hermitian eigenvalue topology is a rapidly growing field of research. And we anticipate that going to higher dimensions using such a synthetic dimension approach will enable many important demonstrations in this field. Now I will switch gear a bit to move to the second approach using isospectral transformations. So the idea of isospectral transformations can be intuitively illustrated by the question on if there exist drums with different geometries that sound the same. And mathematicians show that if you make drums using these two different shapes, they would have the same spectrum, and therefore they are supposed to sound the same. This question is beyond a mathematical curiosity because based on this, one can transform a multidimensional structure to lower dimensions for practical applications. However, I'd like to point out here that even the same drum may not always sound exactly the same. For example, the way that you drum it, which is like how you excite the spectrum, also the way you listen to it, it's like how you select the spectrum. And overall, you don't only need the same spectrum, but also the same weight of each frequency that eventually going into your ears. So, but existing isospectral transformations do not automatically guarantee this. And in this one, we developed a new paradigm using a judiciously tailored Lanczos algorithm to perform a special type of isospectral transformation. So we can transform an arbitrary dimensional lattice to 1D with exclusively nearest neighbor couplings while maintaining the eigenspectrum. And in this process, we are able to choose an anchor site that preserves its local density states after the transformation. Therefore, if you excite this anchor site and observe inside it, the dynamics are exactly equivalent between the two. And this can allow us to experimentally explore the excitation dynamics for hypercubic lattices. So imagine a 1D lattice, 2D square lattice, 3D cubic lattice, and then there will be higher dimensional generalizations that are hard to illustrate. So we can take one of them, run the tailored isospectral transformation, taking the excitation site as the anchor site, and then we realize this using integrated femtosecond laser written waveguides, where the propagation distance day is used as evolution time. And this enabled us to observe single-side excitation dynamics in up to 7 dimensions, but the photonic structure is all within one plane. This approach also enabled us to explore defect localization in higher dimensional lattices. So we found that the single defect exhibits qualitatively different localization behaviors in higher dimensional space. So in 4D and higher dimensional hypercubic lattices, there is a thresholded switching between non-localization and localization, sharply triggered by just a tiny bit of defect strength variation. And such high responsivity may be used for advanced sensing applications. We provided direct experimental evidence of such a prediction using the transformation we developed. And we anticipate that this approach would enable a new class of synthetic planar photonic devices that are mapped from complex multi-dimensional networks. And this platform may also be useful for accessing higher dimensional space in topological photonics, such as the recent demonstration of high order topology. Now I will switch gear again to talk about the last approach, using multiple dimensions associated with multi-photon quantum states. Specifically, I worked on the manipulation of multi-photon quantum states using metasurfaces. So metasurfaces are composed of nanostructures, and it has been shown a very promising new type of ultra-thin optical element in classical optics. The recent efforts are bringing metasurfaces to quantum photonic applications for the generation, manipulation, and detection of non-classical light. We initiated the concept of using a metasurface to manipulate multi-photon quantum states. So we developed a metasurface that can convert an n-photon polarization state to several optimally designed spatial outputs. And the output can be utilized to perform n-fold correlation measurements using single photon detectors, and then we can reconstruct the density matrix of the input state. Such a single piece of metasurface can replace many bulky optical elements or time-consuming reconfigurable measurements in achieving the same task. We experimentally realized this concept and achieved two-photon interference and state reconstruction. In another work, we also designed a metasurface that can perform non-unitary transformations to polarization entangled two-photon states, where we use diffractions as loss channels. So the non-conservative transformation allow us to vary the angle between the two basis states of the entanglement. And as an outlook, we would move towards a versatile meta-optical platform for quantum photonic state manipulation, where metasurfaces transform an n-photon state encoded in the spatial modes as well as other intrinsic degrees of freedom to desired output states. And the transformed quantum state would then be utilized for quantum sensing, detection, or further information processing by other platforms. To wrap up, the shown works span a wide range of optical platforms, from ring resonators to integrated photonic circuits and to nanostructured metasurfaces. Also, they cross time-varying and static structures, nonlinear and linear regions, chromation and non-chromation systems, as well as classical and quantum light. As you can see, there is indeed plenty of space in higher dimensions. With that, I would like to thank all my colleagues, collaborators, and mentors who contributed to the presented works. And thank you all for your attention.
Okay, thank you, Kai. Thank you. You keep the time very successful. So now the session is open for question. Let me check. Please raise your hand and let me see. Sorry. Oh, Professor Alu, please.
Kai, thank you for the great overview, beautiful talk, and great number of papers and of results. I have a general question. You showed 3 different approaches to use these higher dimensions to realize very interesting phenomena in compact devices. Can you elaborate a bit more on your vision of what could be the killer application of this, and where do you see this implemented or making a breakthrough? Many of the phenomena you showed are really basic research phenomena without necessarily a direct application. I would like to hear more about your vision on this.
I see. Thanks, Professor Alu, for the nice question. Yes, indeed, I think these concepts that I presented are so far are on a more conceptual level, but I think they do have a great vision in terms of applications. And for the first part, I think at the moment the non-chromation eigenvalue topology it's still an ongoing theme of research, and and you can see there are many relevant research works nowadays. And I think and people are still looking for, in particular, as an input and output photonic system, which are open systems. How could you judiciously utilize the non-chromaticity other than those trivial non-chromaticity, for example, an overall loss or overall gain, that you could achieve some robust behavior in the operation, and to really utilize that sort of topological invariance. And also, I think these dynamically modulated systems are in general non-reciprocal, and it may be utilized as a device that can convert frequency of light in a non-reciprocal way. And also, I think for the isospectral transformation approach, so usually the network models, and you can imagine they are very, very complex. And that approach allowed us to make the system in a very compact way. And sometimes, for example, when you design something, for example, for sensing with a good responsivity, you may not really think if the structure is really in its minimal necessary size, but that mapping would enable it to be really, really compact. But and on the other hand, I would also like to mention that so the one anchor set is not really the limit of that system. If you are able to enable, for example, long-range interactions in that mapped structure, then you would be able to have multiple input and output ports that respond exactly the same as higher dimensional networks. And that would be possible to realize some multi-dimensional system that are multi-dimensional, but you may not need that many number of input-output ports as that many dimensional system. Okay, I hope that answers your question.
Yeah, question, please. Yeah, Caoyang, please.
So actually, I have two questions. The first one is a quick one. So I think in your third part, the multi-photon quantum states, you combine meta surveys with, I think you involved only 2 photons, right? If I understand correctly, you manipulate, control 2 photons.
Yes, Professor Lu. So the experiment involved 2 photons, but we also theoretically developed the scalability of this system to multi-photon states. And in fact, the number of output ports here needed approximately linearly dependent on the number of photons.
Okay, so I think traditionally we call it multi-photon only if n is larger, equal or larger than 3. And my second question is on the motivation of combining the meta surface with entangled photon states. So nowadays, I think it's increasingly being recognized that we should talk about if we combine 2 things together, they should have some advantage. Or so my question can be reformulated as, if we use meta surveys for this quantum control, is there any advantage it will bring in? And is there any limitation or intrinsic problem it might have if you want to, in the future? I mean, of course, it's conceptually novel, but if you want to do it practically useful, then do you see any future on this direction? You see plenty of space. I want to ask if there's any future.
Sure. Yeah, very nice question, Professor Lu. Thanks. So I think for the first question, that of course, like we in the experiments, we don't have the fancy light source as you developed with many photons, and therefore we tested the feasibility of the approach using 2 photons. But really, the concept was developed for multi-photons that are having a large number of photons, and so the scalability is good for that. And in terms of the advantage of using metal surfaces for entangled photon manipulation. So I think I would like to point one fundamental advantage, that is the interaction of photons with the nanostructured metal surface is very short time. So imagine if you are using a waveguide system to manipulate the photons, and then like even if you just want to add a phase or do a gate, and you need light to propagate in the waveguide for a very long time. But for this system, and it's actually very quick, and therefore as a linear system, you may potentially benefit from the short interaction time where the intrinsic loss of the material is not much seen by the photons. But in terms of, and also because this is a many nanostructures that I think miniaturization and stability is also another advantage that you would be free of aligning many bulky things that stably. So in terms of limitations, I would say that first, so as a metal surface, you are limited to the local element of each of those nanostructures that in the model, usually you don't consider them to be interactive. And therefore, this is a local metal surface. But now there are growing interests in developing non-local metal surfaces that bridges the gap between metal surfaces and photonic crystals. And then the transformations that you could achieve would be much broader. Thank you.
Yeah, okay. Any question? Yeah, Professor Yang.
Hi, Kai, great, wonderful talk. I think it's really creative to use a synthetic structure to study high-dimensional photonics. I'm interested in your first part of work. So for the non-Hermitian system, you creatively used the complex eigenvalue, right, to show a lot of interesting physics. One example to use ring resonator to study the complex winding of the non-Hermitian band, and you did show that. But I'm curious to hear your comments about a unique feature about the exception point about the non-Hermitian system, that is exception points. Did you observe that? Did you see something unique, different at that state when the system is at exception point?
Yeah, thank you, Professor Yang. This is a very nice question. And so I think for this work with only a single energy band, and it may be harder to engage an exceptional point. However, exceptional point is indeed very relevant in this work because there are two models. And in fact, the classification of the inseparable non-Hermitian bands using the braid group is based on the so-called separable band condition. That means the energy bands does not encounter any non-Hermitian degeneracy, which is exceptional points in this system for any momentum k. And therefore, if you would like to transit from one braid to another braid, in other words, to one topological phase to another topological phase, it has to go through exceptional point.
Yeah.
So in other words, so this system, when we measure it, we don't really encounter exceptional point, but the exceptional point is really those the wall that that kind of in between the two topological phases, and that's why this is a very good topologically robust feature.
Got it. That's a very insightful answer. Thanks a lot.
Thank you, Professor. Yeah.
Thank you, Kai. Thank you for the very impressive answer and all the questions from the committee. Thank you. Let's move to the next speaker. Is Professor Lau from the Boston University. The topic is symmetry and topology in photonic nanostructure. Professor Lau, please.
Can you hear me?
Yeah.
All right.
Perfect. Go ahead.
Good morning, everyone, and thank you, Chairman, for the kind introduction. Thank you for giving me the opportunities to present my work today. So my name is Abdullah Dao. I'm new assistant professor at Boston University. I'm new assistant professor at Boston University in electrical engineering department. So today I would like to talk about symmetry and topology in photonic nanostructures. As we know, in the recent years, the demand of miniaturization and integration is Can you hear me? I feel like there is some problem.
Yes, no problem.
Okay, as I mentioned in the recent years, the demand of miniaturization and integration is of great interest, especially the devices that we are using in our daily life, such as GPS, cell phone, and so on. So as an example, today I would like to take the new cell phone as an example. And if you look at the new cell phone in a very tiny space, you can have multiple functions. In order to satisfy such high demand, new integrated optical devices must be compact, highly efficient, multi-frequency band operation, and so on. So in this perspective, we propose a new type of laser that we call topological laser that can have an arbitrary shape, which means that you can densely pack them on chip without losing any functionalities. It is one-way propagation, which means that you don't need additional components such as an isolator to avoid backscattering of the light in the system. And the second part of the talk will be dedicated to exceptional point sensor in a plasmonic system. And the idea here is to use the subwavelength confinement of the light and the enhanced sensitivity of exceptional point to have a new type of sensor that can detect a very low concentration. So I would like to start by what is topological insulator. So imagine you have an insulator material for given energy band, condition band, valence band, and band gap, and you take free electrons within the band gap, they will not propagate in any direction. Basically, you are in gap region or insulating state. However, if you have bulk material with ocean of electrons and you apply magnetic field, they will start to circulate in same direction with the same cyclotron frequency. In this case also, for given energy band, condition band, valence band, and band gap, if you take free electrons within the band gap, they will not propagate in any direction, basically because of vector cancellation. But now, if you look at right at the boundary, you can see some semicircle. What does this mean? This means that if you take free electrons that you put right at the boundary, they will follow the trajectory and start to propagate in forward direction without any backscattering of the light, regardless of the shape of the boundary. In this case, which are quite similar to the quantum Hall effect, we use external magnetic field and cyclotron effect. There are other cases that don't require an external magnetic field, but are based on the spin Hall effect rather than cyclotron effect. So all the story I just mentioned here is based on fermionic system, but it was demonstrated that under specific condition and the specific characteristics such as breaking time reversal symmetry, breaking spatial symmetry, or creating artificial gauge field, some of the fermionic system can be transferred to bosonic system like photons. And this work was awarded by a Nobel Prize in 2016. So there are many groups in the trying to use such a topological insulator in different frequency range, in different platform from acoustic to microwave, or in optics as using ring resonator or spiral structure to show the robustness of topological insulator. So, but this work and many other work in the literature try to show the same, the robustness of topological insulator. But the fair question that we can ask now is, can we use such topological insulator to make a real device? And the response comes in 2017, where the first topological laser in 1D was proposed using SSS model in 1D. And later in the same year, we proposed for the first time that you can have a topological laser using a magnetic material to break time reversal symmetry. Later on, another topological laser was proposed using ring resonator. But again, in the context of miniaturization and integration, it's always good to have a compact device. And if you compare the unit cell of this laser, you can see that it's almost the size of our laser. So how our platform works? What we propose in this platform is to use a hybrid photonic crystal, where we have two types of photonic crystal, star-shaped photonic crystal, which is designed to be non-trivial photonic crystal, which is inside the cavities. And we have arrow-shaped photonic crystal, which is designed to be trivial photonic crystal, the photonic crystal of the cavities. And both of them are made in InGaAsP, which has the highest gain in around 1.55 and bonded on magnetic material, which is the yttrium iron gathered to break the time reversal symmetry. So when we uniformly pump the whole structure in process with external magnetic field, the edge state will be excited, propagate, and eventually coupled to the waveguide, which consists just of removing one line of the trivial photonic crystal. So how we can design such topological laser? In order to do that, we first start with the air-hole-shaped photonic crystal, which is the photonic crystal of the cavities. And we look at the band diagram and we can see that we have a very huge band gap. And when we calculate the Kerr number of the mode below this band gap is equal to 0, which shows that our photonic crystal is a trivial photonic crystal. And the next step is to do it with the star-shaped photonic crystal, which is in the triangle lattice. And when we apply magnetic field, we have a very narrow band gap is open here. And when we calculate the Kerr number of the mode below this band gap is equal to 1, which is non-zero, which means that we have non-trivial photonic crystal. Since the idea is to use indium gallium arsenide to have lasing at 1.55, we have to choose the geometrical parameters of both photonic crystal so that their band gap will overlap around 1.55. So now the next step is how to excite them. What we did is we put the two photonic crystals next to each other, and right at the boundary we put a point source. And by applying magnetic field upward, we have a forward propagation. And by flipping the sign, we have backward propagation, which shows that we can design successfully a topological laser using magnetic material to break the time reverse asymmetry. So the next step is how we fabricate such hybrid structure, which is a combination of multiple material. So what we did is we used 3 main steps of nanofabrication, which is e-beam lithography, etching, and bonding on magnetic material. And as seen here, the quality of the nanofabrication, it is very well done, or the shape of the photonic crystal are very well done. So the next step consists to characterize such photonic crystal to show that we can have edge state. And what we did is we first pump uniformly the whole structure without processing any external magnetic field. And as seen here, we don't have an edge state. And when we apply magnetic field, the edge state is very clear. And in order to know that such edge state correspond to the lasing action, what we did is we collect the output power at the edge of the waveguide and look at how it behaves as function of the pump power. And you see that the emission power we have from spontaneous emission to the lasing action, showing that we have our edge state correspond to a lasing. Again, I mentioned that it is unidirectional laser. So in order to verify that, what we did is we look at the output power, and by changing the sign of the magnetic field, what will happen? And as seen here, when we collect the light in the output of the waveguide, when we have magnetic field upward, we have lasing, and when we flip the sign, we don't have lasing anymore. So this shows that we can design, fabricate, and show for the first time topological laser using magnetic material, even if the magnetic material is weak at that wavelengths. So the next step is to show that our topological laser is robust to any defect, and we can change the shape without losing the functionalities. In order to do that, we propose 2 other cavities when we change the shape of our photonic crystal and photonic crystal cavities. And you can see here we have the edge state very well defined, and we can show that we can have lasing and no lasing by just changing the magnetic field with the isolation of almost 11 dB. I mentioned in the beginning that regardless of the shape of the boundary, we should be able to see lasing. So to prove that, we use an arbitrary shape of photonic crystal, and the design was done in the same way with the same band diagram and the same dimension. And you can see that without magnetic field, there is no lasing, and when you apply magnetic field, the edge state is very well defined, which show for the first time that we can have a laser that can have an arbitrary shape, one-way propagation, and can be arbitrary shape as well. This work was selected as the top 10 breakthrough physics goal in 2017. So this will bring me to the second step of my talk, where I would like to talk about exceptional point sensor. So I would like to begin this part of the talk by comparing Hermitian and non-Hermitian system. As we all know, most of the physical systems are open in nature, which means that energy can flow in and out and exchange with the environment either by radiation or absorption. One of the fundamental differences between Hermitian and non-Hermitian system is the fact that for Hermitian system, the eigenmode do not decay and the corresponding eigenvalue is real. And for non-Hermitian systems, the eigenmode do decay, consequently the eigenvalue is complex. So in the last decade, many have sought to bridge the physics of closed and open system. And this renewed attention underline one of the fundamental difference between Hermitian and non-Hermitian system, their singularities. So in Hermitian system, mod coupled to induce the singularities that we call diabolic point, where the eigenvalue is real. And for non-Hermitian systems, the mod coupled to induce two types of singularities where we have exceptional point and diabolic point at the same time. So what is exceptional point? So it is a special property of non-Hermitian complex matrix. It can be defective at the exceptional point and the eigenvalue and eigenstate coalesce. So now I would like to explain how we can reach such exceptional point in the very simple cases. In order to explain it, I would like to consider a very simple case, a 2x2 non-Hermitian matrix, and use two-ring resonator to illustrate how we can reach such exceptional point. We know in order to reach exceptional point, you need two physical parameters, and the two physical parameters that we will select here will be the radius, which will determine the resonant frequency, and D, which is the distance between the two resonators, which will determine the coupling coefficient. Since we have a non-Hermitian system, we have both real part and imaginary part. So the idea here is to look at how the real part and the imaginary part will behave as function of the two physical parameters, which is R and D. So to do that, what we did is we look at how the real part and imaginary part as function in R and D, and we have very nice Riemann sheet in both cases, imaginary part and real part. And on one side, you can see that we have crossing, and the opposite side, we have avoid crossing, which is the inverse in the imaginary part. And if you look at very carefully this Riemann sheet, there is only a single point where you can have both real part and imaginary part exactly the same. This is what we call exceptional point. So to show how exceptional point is important in terms of application in optics and photonics, I would like to show some applications that are recently done in exceptional point that Professor Young did a lot of great work on it. So to show the single mode lasing, no reciprocal devices, it is done also for chirality and especially for sensing using gyroscope or sensing of second order of exceptional point. And recently, back to back, we have two nice papers on Science showing exceptional point in holography or perfect absorption. So again, exceptional point is done in different frequency range from acoustic to microwave and in optics using dielectric, which is subject to diffraction limit. Now the fair question that we can ask ourselves, can we have such exceptional point at sub-wavelength scale in a plasmonic system? And why we need exceptional point at sub-wavelength scale? In order to respond to that question, I would like to go to the next slide and compare the two singularities when they are subject to perturbation, and the perturbation here is epsilon. And as seen here in blue, when we consider the singularities of both Hermitian and non-Hermitian system, which is diabolic point, you can see that the frequency shift is always linear to the perturbation. However, for exceptional point of second order, you have square root behavior, third root behavior for the exceptional point of third order, which shows that when you increase the order of exceptional point, you have more sensitivity than the diabolic point. As we know, plasmonic system can confine light at sub-wavelength scale. So the idea is to use the sub-wavelength scale confinement of the light and the enhanced sensitivity of exceptional point to have a new type of sensor that can detect a very small concentration. How we design such a structure? As we know, when you pair two gold bars in close proximity, you hybridize the plasmon mode in two modes of opposite symmetry. Oscillating in phase, you have a symmetric mode. Out of phase, you have antisymmetric mode. And we know that the spectral position of this mode can be tuned by spatially shifting one bar respect to the others. And as seen here, when we start, we have the symmetric mode in the high frequency, which is radiate more, and the antisymmetric mode in the low frequency. And as seen here, by shifting one bar respect to the others, the repulsive character of the symmetric mode will weaken to become attractive, and the opposite will happen in the antisymmetric mode. And by keep shifting the value of dx, at some point, you will have the two resonances will cross, and that shows that you can have resonant crossing by just controlling the shift of the two bars. We know in order to reach exceptional point, you need two physical parameters. But the two physical parameters should change both the real part and the imaginary part. How we can find the second physical parameters to reach exceptional point? What we did is we consider a very simple case. We have one metal bar on a dielectric, and we look at how he behaves as function of the periodicity, which is perpendicular to the length of the bar. And you see that both real part and imaginary part are changing, which means that this parameter can be used to reach exceptional point. So this will be the second parameter. And now, since we have all requirement to have exceptional point, the first configuration that we propose is to have two bars with the same size embedded on dielectric. But surprisingly, if you look at the both real part and imaginary part as function of the two physical parameters, only the a real part show a crossing and the imaginary part is completely different. We don't have crossing, which show that, which is obvious because we are using two modes with opposite symmetries. Their loss rate are completely different. So now the question is how to reach exceptional point since we have all requirements. In order to reach exceptional point, in this case, we have to have the two modes that have loss a little bit close so that physical parameters can make them exactly the same. And to do that, what we have to do is we have to break the symmetry of the structure. And breaking the symmetry here, what we did is we take one bar smaller than the second one. And in this case, by changing the physical parameters, we can reach exceptional point. We have crossing and avoid crossing on one side, and in the imaginary part, the opposite. Again, the idea is not just showing the existence of exceptional point in a plasmonic system, but being able to use it for a sensing. And how we did that? Since this is embedded on dielectric, which means that the confinement of the light will not be in contact with the analytes that we would like to sense, what we did is we have a new configuration that have two bars with the same size, but how we break the symmetry is we put one bar embedded on a dielectric, which is as if that the one bar on air and the bar on dielectric don't have the same size. And in this case, we can reach the two goals, which is having exceptional point and being able to use it for a sensor. And this is what we did, and we show the existence of exceptional point. So our proposed platform is an array of metal bars, one embedded on a polymer and the second one sitting on air. And here we show the successful fabrication of the nano device using 3 steps of nano fabrications. And we show that we can control very well the geometrical parameters of our structure. So now how to characterize such exceptional point? Since we know exceptional point is always between crossing and avoid crossing the position, we choose two PY, one higher than the exceptional point and one lower than the exceptional point, and we do the measurement to compare with the numerical simulation. And we see that we can have crossing and avoid crossing in loss rate and the opposite. And when we compare it with the numerical simulation, we have a very good agreement between them. After successfully showing that we have exceptional point for the first time in plasmonic system, what we did is we use it as a sensor, and we use the immunoglobulin J, which is one of the common antibody in our human body. So what we did is we functionalized the top of the bars with the antibody, with the anti-IgG. And what we did is we consider a concentration of 1,000 attomolar, 1,500 attomolar. And we can see that when the concentration is very high, which is relative because 1,000 attomolar, 1,500 attomolar is very small, but is not the regime where exceptional point is better than diabolic point. So by being on the regime where exceptional point is better than diabolic point, which means that by progressively decreasing the concentration at 1,000 attomolar, we start seeing that exceptional point is much better, is better than diabolic point, and by progressively decreasing it, we see that the difference increase. In order, again, to prove that we are at exceptional point, we consider the concentration as the epsilon, and we look at the behavior of the two modes, and we can see that exceptional point have square root behavior and diabolic point have linear behavior. And this shows that we successfully design and have an exceptional point. And we detect a concentration, which is 15 10 to the minus 9 nanogram per milliliter, which is almost 300 times better than the state of the art. So to conclude the talk, I have many other works that I didn't have time to present today. I would like to say we successfully designed and shows that we can have exceptional point in the plasmonic system, but we also shows that we can have the highest bandwidth meta lens using a meta surface with a single layer. And this work was selected as one of the most read paper in Nature Communications. By using the physics of topology also, we show for the first time a topological laser that was selected at top 10 breakthrough physics world. We recently showed in last 3 months that we can also generate a large topological charge of orbital angular momentum using topology, the same principle that we use for the topological laser. I would like to thank all my previous lab where I did my postdoc at UCSD and UC Berkeley in Kante Group, our collaborator, Professor Connie Chen, Saya Feynman, and Yualu. And for that, I would like to thank everyone. 谢谢.
Okay, 谢谢. Very impressive talk. So now the session is open for question. Check it. Oh, Professor Jagadish.
Thank you, Professor Sao and Abdullah. Very nice talk and very nice work. So I have got one simple technical question, and so then I have the other question about what type of powers you are able to get from these topological lasers, and then what do you see as limitation in terms of getting high powers?
That's a good question. The power that we are getting out of this laser is very low. It's like a milliwatt output. But for the beginning, when we are working on this, the goal was not to have a good performance, but to show the physical principle. And here we have to open the band gap using a magnetic material which is very weak in the optics region. So, and we use an interlayer between the magnetic material and the gain material to do the bonding, which is a polymer. So if we hit it a lot, since the three materials don't have the same conductivity, they don't have the same parameters, we can burn the sample. So in order to make it like powerful, I think the best way is first to be able to do it in the CMOS compatible way, instead of having an interlayer, which is a polymer that don't have the same coefficient as the other material, to do directly bonding, or to etch directly the magnetic material, which is very challenging. We know how etching magnetic material is challenging, so that the confinement of the mode and the gain, we will have the way to open a larger band gap. We also will have the possibility to use the gain without doing nanostructure. And again, the next step can be to have it electrically pumping, which we can control also the current. But for now, the output power is very weak.
Okay, good, thank you. And you're also using disparate materials, and you're doing the wafer bonding. How you're really putting these quantum wells onto this GGO and IG and other things?
That's what I. So in order to do the bonding, what we did is we spin coat on top of the IG material, because we bought the IG material on top of the GGG, and we spin coat polymer on top, very thin layer, less than 10 nanometers, and we do the bonding on top. So we do bonding using a polymer, which is not the fair method to do it. It's the industrial way. We should do it in the by doing it in direct bonding, which we will treat the surface, and so that we will don't have any interlayer between them.
Okay, thank you.
Okay, Professor Alu.
Yes, thank you, Abdullah. You did you had a great presentation.
Thank you.
My question is about your exceptional point sensors.
Yes.
With plasmonics. So there is an ongoing debate about whether a passive sensor working at AP can be better than a passive sensor tuned at the right resonance, not operating at AP. Can you elaborate if you have any insight into this, and how, if you actually believe that operating at AP is important, and you can clearly observe a merit to work at the square root slope of your extracted fit with the tuning as your measured parameter changes.
Thank you very much. I think this is a very interesting question as well. But what we have to know, this is like an ongoing debate between people doing exceptional point and no exceptional point. And recently there is many papers coming out. Some are showing that exceptional point at some regime can be better than diabolic point, as are showing the opposite. But what we have, in my opinion, is so far, all exceptional points that experimentally done showing sensing are showing that a performance that is better than a normal sensor. The second thing is people are talking a lot about the noise in the quantum domain, but when exceptional point was done, it was for the classical domain. And in the classical domain, I feel again, based on all experiments that are done, we show that there is a good like exceptional point outperform to the normal sensor. But again, I think going to the quantum domain and having, for example, a quantum entanglement sources, using it with exceptional point can be a very nice direction that people should investigate. But again, there is no clear way showing that if exceptional point in the quantum regime will not be better than dipole point and any normal sensor. But so far in the classical domain, exceptional points show a very good result.
Yeah, so thank you. So Professor Oskin.
Thank you for this beautiful presentation. So I had a question regarding your sensing results with EP. So first, what constitutes the ground truth in your measurements at those extremely low concentrations? I'm curious to see what repeatable method you used to establish the ground truth. And a related question is, are these measurements done with serum samples or spike samples? And how do you envision this system working with real samples and all the background proteins, etc.? So would you be able to utilize the sensitivity that these plasmonic structures are providing to you in real samples where other matrix effects will set the noise floor of your sensor in a practical application?
Yeah, that's a great question. If I just can come back to so if I can come back to your first question, how we can control like the sensing and knowing that what we are doing is really what we are sensing. If I can summarize the question in this way, what we did in this sensing is we functionalize the top of the bar with the linker, which is fully saturated. So when we functionalize it, we have a shift of, for example, 5 terahertz. And from that, any concentration that you put that is below 5 terahertz terahertz shift of the delta wavelength cannot be detected. And after we keep adding the concentration, and by adding the concentration, any concentration that bring you higher than that value, you can see it on the detection. And after what we did is, when we finish one concentration, we have a system to clean the sample and do measurement again to be sure that we are at EP. Because again, we cannot be at EP because since it is singularities, but you have just to be close to the EP, as close as you can, so that you have highest efficiency. So what we did is, for each measurement, we functionalized, we cleaned the sample, and we did measurement again in the same way, so that we know exactly where we start. Because if after functionalization and you clean your sample, you did the measurement, you don't have the previous result, which means either you damage your sample or there is something attached on your sample that you are sensing at the same time.
What constitutes your ground truth measurements? Meaning that you say you induce a certain concentration, but how do you know that that concentration is that concentration? And what is the standard deviation in your ground truth?
So how I know that the concentration is exactly the concentration on my sample?
Yeah, so for any y equals x measurement, right, there is y at the ground truth. So what is your measurement error on ground truth? Because that's what sets your sensor's performance. For example, if I were to work with clinical samples, my measurement device from clinical system, FDA approved, will be my ground truth, and I'll be comparing it against the ground truth.
Okay. So what we did here is, when you functionalize the top of the bars, since we have the anti-IgGs that we can like put a quantum dot on top of the sample. that we can image and count the number of quantum dots on top of the sample and seeing how many anti-IgGs that we have. This is the first measurement that we did by looking in a microscope, and we can count the number of quantum dots that we have on top of the surface that we will compare in the concentration that we have. In any step of the fabrication, we will have quantum dots and look at in a microscope and like do a post-processing that will tell us the number of quantum dots that can fix on the anti-IgG.
Well, but that's not the concentration in the liquid. That's the concentration indirectly measured on the surface. And
yeah,
that I think is...
The concentration in the liquid, what we did is we look at the number of concentration, the volumes that we have on the sample. Mm-hmm. Like we have a sample, for example, the samples that we use is 1 centimeter by 1 centimeter. What volumes that we should consider, what concentration that we have. We calculate what volume we have, what mole numbers that we have, and from that we calculate the concentration.
Yes, but experimental, that system has errors. So whatever you're infusing, whatever you're pipetting, whatever you're injecting has an error. And yes, that's going to set your standard deviation. I'm trying to understand volumetrically, not surface-wise, volumetrically, what is the concentration error that you have in your ground truth?
In this case, the only measurement that we did to be sure for the concentration is done is we take any samples that we are doing the measurement, we do like 10 times the same concentration and see that if the variation is changing based on the ways that we did the concentration calculation or no. And we still have almost the same, and the error bar is very small in that case. That's the only way that we did.
Thank you.
Yeah.
Thank you. It's very important to do the calibration when you are,
yes,
you are using sensing. Yeah, thank you very much for the nice talk and the answers. So let's move to the last speaker. Is Professor Kapo from the Swiss Center for Electronics and Microtechnology. The title is the Dynamics and Applications of Soliton Microchromes.
Thank you. Can you hear me? And can you see the slides as well?
Sure.
Cool. Thanks a lot. Hi, everybody. My name is Maxim Karpov. I'm actually a postdoc in the Swiss Center of Electronics and Microtechnology. And it's a big pleasure to be here today and talk about the technology I worked over the past few years. It's optical microcombs, which are optical frequency combs based on optical microcavities, microresonators. And particularly, I will be talking about soliton microcombs, which are microcombs based on resulting from the soliton formation in these optical microcavities. So the soliton microcombs as a field appeared around 8 years ago. And since then, they experienced explosive-like development, moving very quickly from their first experimental demonstration towards the understanding of their physics and actually towards even the real-world applications. And I was very fortunate to be a part of this journey and contribute to this journey. And so this is my talk about this journey. So I'm going to start with the brief introduction to what is the soliton microcombs. Then I will move to several physical effects, dynamical effects, which we discovered. And then we also, I will cover several first demonstrations of the soliton microcombs applications to a variety of fields which we developed. So let me start with the in general optical frequency combs. So it's optical sources which spectrum consists of a series of distantly spaced optical frequencies, which can be actually described as just 2 parameters combined in a very short expression shown here. It's the repetition rate frequency corresponding to the spacing between the adjacent lines of the comb, and the offset frequency, which corresponds to the offset of this frequency grid with respect to 0. And the main feature of the optical frequency combs is that they actually enables the phase coherent link between these lines in optical domain and these 2 frequencies in the RF domain, which can be directly measured. And sometimes you can think about the optical comb as a ruler in the optical domain. And these 2 gentlemen were awarded Nobel Prize in Physics for the development of the precision laser spectroscopy and optical frequency combs. And one of the very interesting techniques to generate optical frequency combs was shown with the help of optical microresonators. So these are millimeter or micrometer scale optical cavities, which are able to confine light due to the effect of the total internal reflection. And due to their high quality factors and intrinsic nonlinearity, when you drive these systems, these microcavities with a continuous wave driving field, you can actually achieve very strong intensities inside the cavity, and you can enable the frequency conversion process, in particular for its mixing process, which start to populate other cavity nodes with photons, kind of building the optical lines in this around these cavity nodes, and contributing to the building of the optical frequency comp with equidistantly spaced optical lines. And such optical comps, they called Kercomps or microcomps, and they were actually demonstrated a number of platforms in comparison to the standard optical frequency comps based on fiber lasers and mode-lock lasers. They actually, they can be quite compact because they're based on micro-resonators, and the second, they provide access to very large repetition rates ranging from gigahertz to a terahertz domain. One of the very important steps in the field was the demonstration of soliton microcomps. And the idea is that under some certain conditions inside the cavity, the light can actually self-stabilize in the form of the soliton pulse, which kind of circulates inside the cavity stably. And it happens due to the double balance between the dispersion and linearity on one hand, and the driving, continuous wave driving, and the cavity losses on the other. And the output of the cavity, this optical pulse train, in time domain corresponds to the formation of this kind of highly coherent optical frequency comp, soliton microcomp as we call it. And the system can actually be described with a very simple equation. It's a nonlinear Schrödinger equation with damping and driving, which is also called Lefebvre equation, or LLE. And it was shown that LLE indeed has a soliton-like solutions with some continuous wave background in these micro-resonators. So these soliton microcomps, they were demonstrated in a variety of photonic platforms, micro-resonator platforms, and I would like to particularly highlight one of them. It's a silicon nitride micro-resonators. Why? Because due to their wide transparency window, high effective nonlinearity in comparison to silicon, for example, yes, and combined with the very with fabrication process which enable very low loss optical waveguides, they actually became this silicon nitride microresonators became one of the main drivers of this soliton microcomps. And in my further slides, the majority of the dynamical effects and also the majority of the applications which we demonstrated was actually done with the help of this silicon nitride microresonator soliton microcomps. Now let's move to dynamics of soliton microcomps, which we worked at. The first dynamical effect is the Raman-induced soliton self-frequency shift. So it turned out that the third-order nonlinearity in microresonators, which enabling the forward mixing process, it can also enable some third-order inelastic process, such as simulated Raman scattering. And this simulated Raman scattering usually happens within the pulse, where essentially takes the photons from the high energy part of the pulse and transfer to the lower energy part of the pulse with the emission of the photon. And this process is actually very well known in optical fibers, where it results in continuous shift of the soliton spectrum with respect to kind of its initial position. So the spectrum continuously shifting towards the red once the soliton propagates inside the optical fibers. So in our experiment, we actually demonstrated that soliton microcomps have completely different, but drastically different behavior of in response to Raman effects. So first of all, we also observed that the Raman shift is present there, but surprisingly, the Raman shift was fixed, and it was not changed as the soliton propagated inside the cavity. So we also demonstrated that the soliton shift does not depend on the pump power, and it's only essentially, it can be only controlled by the changing of the tuning of the laser with respect to the cavity. We also developed the framework to explain and demonstrate these features theoretically, and we also showed that it's indeed kind of the real features of the soliton microcomps, that the soliton self-frequency shift is due to Raman effects is fixed in these devices. And beyond the physical significance of this understanding of how Raman effects impact the dynamics of the soliton microcomps, it also helped us to understand some limitations on the operation of the soliton microcomps and also predict their spectrum envelope properties. The second unique effect, which we also discovered, was the so-called soliton switching. And the idea is that one of the issues of the soliton generation process, which is shown here, which consists in essentially taking the laser and tuning it over the cavity resonance and then trying to find and land on this characteristic so-called soliton steps, is that once you implement this process, once you land on the soliton step, usually you end up having the multiple solitons inside the cavity. And in this case, the resulting spectrum usually have this very unpredictable, very kind of structured spectrum, which is hard to use for any applications. And it turned out, what we discovered is that very simple technique of adding additional tuning step in a reverse direction can actually help to deterministically reduce the number of solitons inside the cavity, removing them one by one. As shown here, we go from 3 to 2 to a single soliton state. And it's turned out to be very important because it essentially opens up an on-demand access to a single soliton step, which is application relevant because of its smooth spectrum envelope and essentially like very low line-to-line variation. So we're trying to understand this behavior, and we developed some special tuning techniques based on the network analyzer modulation of the microresonator. And we understood that this behavior is highly linked to thermal effects of the cavity. Some of them on the thermal effects are kind of, if you imagine to cross out the thermal effects out of the cavity, then all the soliton states for different soliton number, they are degenerate in terms of the tuning. However, once you turn on the thermal effects, then the states with higher soliton numbers, they start to move with respect to lower soliton number states because of the thermal shift. And essentially, it's opened up this kind of very peculiar stepwise pattern, which essentially opens up the access to a single soliton state. And as already mentioned, it's turned out to be very important because first, it essentially enables the access, like on-demand access to the soliton states with any number of solitons, and essentially opening up a very wide field for their investigations, their statistics, for example. Second, it's that it's opened up the access to a single soliton state, and as you would see further in all of our applications we demonstrated. In my which I will be talking about in my following slides, actually they're all based on a single soliton states, and essentially this soliton switching effect, soliton switching behavior was then enabling dynamics to enable all of these applications. The final dynamical effect, which I'm going to talk about, is the so-called soliton crystals, and it turned out that solitons inside the cavity, they can form this sort of ensembles of solitons with a long-range temporal ordering, and by the analogy with a crystalline state of matter, they were called soliton crystals. And the reason behind these formations is that it's so-called avoided mode crossings in microresonators, which can selectively enhance some of the optical lines, and which, by beating with the pump, can induce certain modulation on the background inside the cavity. And this modulation can essentially pin the soliton in place and kind of withhold them as they circle around the resonator. So what we demonstrated is that, in fact, this soliton crystal states, they can actually fully fill the cavity, forming so-called, kind of closed optical soliton lattice with exactly distantly spaced solitons. And we call these states perfect soliton crystals. And what is cool about these perfect soliton crystals? Well, several things. First is that the resulting optical comp will have the multiple FSR spacing, where the scaling factor corresponds to the number of solitons inside the cavity. Second, every line of resulting comp will get an squared enhancement of the number of solitons in terms of the intensity in comparison to a single soliton state. And here, just to demonstrate, is that, for example, we had a device where we got almost 100 solitons in this perfect soliton crystal state, and every line got almost 40 dB enhancement in comparison to a single soliton state. So it's a really increase, like boost in the conversion efficiency of these soliton states. And the third is that we figured out that currently these perfect soliton crystal states, they can be deterministically accessed in almost every device. And this is actually demonstrated also on the right, is that we took different devices with very different properties, different fabrication processes, and we managed to demonstrate in every of them the perfect soliton crystal state. Apart from having these amazing features, we also figure out that the dynamics of perfect soliton crystals is quite peculiar one. We observed, for example, the switching of these perfect soliton crystals as for the regular soliton states But the cool thing was that we can actually switch between perfect soliton crystals, going from soliton crystal with 15 solitons to 13 under some certain conditions if you properly treat the system. Another cool thing which we observed is a so-called disordering and melting of the crystals, which actually was reversible. So we can, by tuning the pump, we can actually introduce some disorder into the system and even lead the integrative field to sort of the Brownian-like motion of the solitons. But then you can also tune it back and reverse the initial state into the perfect soliton crystal state, which essentially would be the same as you had before. So kind of you can melt and recrystallize the soliton crystal state. And what we understood is that all of this behavior is tightly linked to the stability diagram of the system. So essentially, it's different states in the map of detuning and the power of the system, which turned out to be quite complex. So we experimentally discovered several new regions, so-called transient chaos, spatiotemporal chaos, which turned out to be adding a lot of complexity in the dynamics, not only perfect soliton crystal states, but even just regular soliton states. We also worked in a number of other works on other topics in soliton microcombs, including soliton breezers and other things, but I'll decide that I will stop here for the dynamics of the soliton microcombs, and I will move towards their applications. So the applications are somewhat condensed in this slide. And as you can imagine, this applications of soliton microcombs very similar to applications of conventional optical frequency combs. However, due to their advantages of the microcombs, such as their compactness and access to very large repetition rates, they particularly can be interesting for applications in communications, like for telecom data centers, and also, for example, for the generation of low noise microwaves. And so in our work, we demonstrated, we make several first demonstrations of the microcomb potential in some of these fields and even beyond, which I'm going to cover in my next few slides. So the first thing we demonstrated was the operation of the soliton microcombs in a new operational window. So before our work, all the microcombs were mostly working at around 1550 in the telecom wavelengths. But we demonstrated that silicon nitride platform can actually enable the generation of soliton microcombs at around 1 micron. Why it's important? Because the wavelength region between 700 and around 1400 nanometers is very important for biomedical applications because it has the light here has the highest penetration depths in tissue. And apart from demonstrating that we can generate the solitons in this region, we also demonstrated that we can design devices which enable them kind of the octave spanning soliton states. Why it's important? Because it can help to make self-reference the soliton state, essentially stabilize its omega repetition rate and offset frequency. And apart from doing this, we also showed that such COMBs can cover an important atomic transitions of cesium and rubidium, which are used for optical atomic clocks and laser stabilization. Another very cool application, which we demonstrated, was for optical coherent communications. And two main features of the microcombs is that they are able to provide the access to these high repetition rates. In particular, it's important because for example, the access to the 100 gigahertz spacing enables the using of the microcombs for communications because it matches to the dense wavelength division multiplexing frequency grid of 100 gigahertz or 50 gigahertz. And so in the collaboration with the University of Karlsruhe Institute of Technology, we took two soliton microcombs and using actually only the middle part of the spectrum, we managed to demonstrate a massively parallel coherent communication using the soliton microcombs. And we actually achieved really high accumulated data rates of about 55 terabit per second using two soliton microcombs. And it was the first demonstration of soliton microcombs for optical communications. And actually, I just wanted to mention that this was actually the world record for a comb-based system at the time for the optical communications. Another interesting application which we demonstrated was the distance ranging, ultra-fast distance ranging using soliton microcombs. And it's again due to their large repetition rates and very wide bandwidths, they can actually enable the very fast data acquisition of the distance, or very fast distance measurements. And the approach we used is called synthetic wavelength interferometry, which was implemented with kind of in massively parallel manner using two combs. One was used as a signal comb, and we shoot it towards the target. So if each of the comb lines has acquired some phase shift due to the propagation forcing back, and then we uncovered this phase information using the LO, the second comb, LO comb. And by doing this, we were able to achieve very high acquisition speeds of about 100 megahertz. While having the precision on the order of like 300 nanometers. And while increasing the average in time, we can actually go down to 12 nanometers with about 100 kilohertz sampling time. But the coolest part of this experiment was that we actually took an air gun and we shot a bullet through the beam of our measurement beam. And the bullet was flying around 150 meters per second, and we were able to precisely recover its profile. So it was it was the first demonstration of certain microcombs for distance measurements for LiDAR, and it was one of the fast optical measurements with sub-micron precision. And the final application which I would like to cover is the application of certain microcombs for photonic computing, and particularly for computing of the convolutional neural network. So it turned out that microcombs can actually help to parallelize the computing of the matrix spectral multiplications in a system based on a photonic electric surface with a phase change material. Actually, Carlos already mentioned this work today. And so essentially, we developed the microcomb system. We built it, and together with University of Münster, we use it to implement two experiments. In the first one, we use this optical condition operations to apply certain sort of edge filters to the images, and also including some edge detection filters and some other filters. And in the second part of our experiment, we also did sort of the handwritten digit recognition, where the main part, the convolution part, was done optically using our system. And so that was the first demonstration of microcombs for photonic computing. And we also demonstrated that combining the silicon nitride technologies with photonic, with phase change materials, we can actually develop the fully CMOS compatible photonic hardware accelerations, which can access really high number of multiply accumulated operations per second. And with this, I would like to finish my talk and thank all of my colleagues from APFL and KAT, CSCM, and the University of Münster and the Russian Quantum Center. I particularly would like to also thank two people, as Professor Tobias Kippenberg, with whom I did my PhD, and Professor Michael Geradziewski, with whom we had a lot of pleasant discussions and about the certain microcombs and their dynamics. And I would like to thank you for your attention. And yeah, I'm looking forward to questions.
Okay, thank you. Thank you for a very impressive talk with Michael Korps. So now the session is open for question.
Okay, can I ask a question?
Sure, Professor Cao. Yeah.
Hi, great talk. So I have a question about this application for LiDAR, which you mentioned. So how much power can you have, eventually, or how many also parallel channels you can have?
Yeah, just in this particular experiment, we use a lot of power. So the output power of the microcomp, usually the total power here in the order of like 1 to 10 milliwatt for the full comp. So we used a set of amplifiers. So we used two-stage amplification to bring the power to I think the watt level, as far as I remember, for the full comp, to essentially get it to the target and then efficiently have essentially enough photons to measure and beat it with the LO comp. Well, on the other hand, also the amplification of the local comp can help. And as you can see, we could recover. So this is actually this is a spectrum of the so-called dual comp spectrum. When you essentially on the one bounce photodiode, you overlay two comps. And here we were able to get some decent signal of about maybe 30 dBs for I think it's about 100 or 80 lines roughly. But but that's true. The power, so we have to use additional amplifiers to get a good signal to noise. Did I answer your question?
You had using a broadband amplifier in order to amplify.
Yes, it was a C+L band amplifiers to, I think, from 1500 to 1600 roughly.
Okay, thank you.
Actually, if you look at this spectrum here, you see the cut. I mean, maybe here, for example, the spectrum which is unamplified, right? So you can see that it's actually, it has a lot of maybe 300 lines in total. But if you look at this spectrum, you see it has a lot of cuts at 196 and 885, and the cutting actually comes from the amplifier here.
Okay, thank you.
Thank you. Any question? Yeah, Professor Yang.
Thanks for the great talk. Silicon has been a hot topic for a couple of years in the past. I'm curious to hear comments about the silicon nitride you choose for your platform, because there are many kind of cavity cone generated in the platform made by silicon. And can you comment on that from the point of view of ease of fabrication and also nonlinearity physical properties, and tell us, in your view, is silicon nitride really the most promising platform for cone generation?
Well, I was mostly working with silicon nitride, so I would obviously advocate for silicon nitride performance. But I know that silicon nitride sometimes has some. It might be easy. It might be difficult to fabricate. It's less mature than, for example, the standard silicon photonics processes, and but it has its own advantages in terms of like very low loss platforms, very low losses. Because, for example, they're reporting I think 30 million quiz, which corresponds to less than 1 dB per meter, which I'm not sure if that was demonstrated with silicon photonics. Then it has a higher nonlinearity than silicon, which is also helps. I mean, in particular, I mean, if we're talking about, I'm talking from the perspective of nonlinear photonics, right? So where from the perspective of soliton microcoms. Of course, for linear photonic applications, the silicon photonics would be much more easy to fabricate. It's much better developed technology than silicon nitride. But from the perspective, I'm talking from the perspective of nonlinear photonics. And so it's the high nonlinearity transparency window. Also, there's a lot of works for the dispersion engineering has been done to show, so we know how to boost the spectrum of the soliton microcoms in silicon nitride. We know how to move them to 1 micron, and in principle, I believe that we can. Actually, I think there was a demonstration at around visible wavelengths about 700 nanometers, and I believe due to the high band gap of silicon nitride, we can even move it down to visible. So I'm just looking from the perspective of silicon, from a nonlinear photonics, and I would advocate for silicon nitride. But I know that there was a lot of demonstration of soliton microcoms for example, in silicon, which was done by Gita Group in Cornell, and silicon might be interesting because it enables to move towards the mid-infrared comps, which silicon nitride cannot do. I think that's I think the furthest we could go around 2.5 micron. In terms of, I also know there was interesting works with Hydex materials, and the solitons is using the Hydex platform. Unfortunately, I haven't worked with this one, but as far as I remember, it has a comparable nonlinearity with silicon nitride and also comparable losses. But I'm not sure actually what was the lowest losses that I achieved with the Hydex material.
Yeah.
Yeah, there are also some other new platforms like lithium niobate, aluminum gallium arsenide, and many others where the silicon was demonstrated. But I think all of them, they are more very kind of research and initial stage of their kind of development.
Got it. Thanks a lot for sharing your thoughts with us.
Yeah. Any question? Well, may I ask a question? You have the source for the imaging, ranging, and also this successful applications. Do you have other plans and for other applications in the near future? And also you have very less papers and get very high citations. So do you have some plan to transfer your technology to the industry? Yeah,
that's a very good question, and we are partially working on it right now. So this is actually one of let's say our topics. So we would like to actually, that's maybe the slide I forgot to jump on because I was not sure about the timing. But that's actually one of the our current directions is that we would like to make the solid microcom. Well, first of all, in order for them to be picked up by the industry, we would like to make them smaller. We would like to make them turnkey. This is important because so far it's the lab grade setups in the labs which has to be operated by PhD students. So we like to make them smaller. You want to make them turnkey. And then concerning the applications, the most potential we now see in a data center applications and in telecom because as I mentioned, they are matching this dense wave diffusion multiplexing grids, and they can be used to kind of boost the data speeds for the communication either within data center or outside of the data center or between the data centers. And for example, one work which actually didn't mention here, we did a really cool demonstration with Microsoft Research on employing the Soliton microcoms, for whom we developed a kind of turnkey system to use it for data center networks. So the idea is that the Soliton microcom can actually replace the complex hierarchy of electrical switches inside the data center, and instead we can use the optical switch based on Soliton microcom. And we actually demonstrated with Microsoft, and the paper actually is coming out soon in NatureCom.
Okay, thank you, Maximum. Thank you.
Yep, you're welcome.
Answer. And looking forward to your new progress and achievements.
Thank you. Thank you very much.
From the committee. Okay, thank you, Maximum. Yeah. So thank you for the presence for more than 3 hours. We have a big morning and a big light. We have 6 gorgeous presentations by 6 rising stars in photonics, in light. And we have so many challenging, tough, and last questions from 7 science in our award committee. The biggest award in this event is the valuable questions and the source of wisdom from our committee, top scientists and the giant stars in the universe of light, optics, and photonics. I hope all of you enjoy the talk and enjoy everything. The stars are rising. The first session is ending, and the second session is coming. So we are looking forward to the second session next Friday, as well as the award ceremony. On October 15th, we will have another 4 emerging stars, Jonathan, Igor, Qifan, and Ning Yan at 8 p.m. Beijing time. So 2021 Rising Star of Light award ceremony will be held at 10:30 p.m. Beijing time. So good luck to all the finalists. So ladies and gentlemen, colleagues and friends, this is a Rising Star of Light. This is light. This is Enc. So enjoy the weekend, enjoy the breakfast, and good night. See you next time.